What if everything you believe about time is just a side effect of being human? That space isn't a silent backdrop, but a restless fabric, stretching and bending with every massive breath of the universe. That your past, present, and future don't actually exist as separate moments, but as illusions stitched together by a brain trying to make sense of the chaos. What if clocks lie, memories shift, and what you call now is already history by the time you feel it? These aren't philosophical riddles, they're scientific revelations. In the next 4 hours, we'll unravel the hidden dimensions of time, question the flow of reality, and explore the strange playground where quantum fields, perception, and gravity collide. So if you're ready to unlearn what you thought was certain and glimpse the invisible strings pulling your sense of self, tap like, hit subscribe, and let's descend into the paradox of existence itself. You are living in the past. You've never seen now. What if I told you that everything you've ever seen, every color that passed before your eyes, every movement, every smile, every sunrise, every person you've ever loved, happened already before you noticed it? And what you're experiencing as now is always late. That you are not living in the moment at all, but in a filtered, delayed, carefully constructed version of reality your brain stitched together to keep you sane. It sounds impossible, like a glitch in perception, a poetic exaggeration, but it's not. It's a cold, measurable, scientific truth. You, the person sitting or lying here, listening, watching, breathing, are perpetually lagging behind reality. Not metaphorically, literally. Your experience of the world is always a reconstruction, a shadow of what already happened. Because light, the very thing that lets you see, travels fast, but not infinitely fast. Even the light bouncing off the phone in your hand, the face of a loved one, or the sun in the sky takes time to reach you. Nanoseconds, milliseconds, or minutes, depending on distance. But more crucially, when that light finally touches your eyes, it still has to be processed. It needs to be converted by your retina into electrical signals, sent through your optic nerve, filtered by your thalamus, and then interpreted by your visual cortex. By the time your brain forms a visual image, the event you're observing is already in the past. Every glance you take is a look backward. You are not experiencing reality as it is, but as it was. And that alone is enough to distort everything. You think you know about time, presence, and what it means to be here, in the now. But it goes deeper. Not only do photons take time to reach you, and neurons take time to fire, your brain actively delays your reality. It does this so that the sounds you hear, the sights you see, and the sensations you feel can be synchronized. If your brain showed you the raw, unedited feed of the world, it would be chaos, like watching 50 unsynced camera angles of the same movie, all playing at once. So instead, it waits. It holds back fragments of data for milliseconds, then binds them into a single cohesive moment. That binding delay is your present, but by the time you experience it, it's already gone. And this isn't speculation. It's been measured. Neuroscience experiments have shown that your brain takes approximately 80 to 100 milliseconds to generate your conscious experience of an event. That means when you think something is happening now, it happened almost 1/10 of a second ago. Enough time for a bullet to travel dozens of feet. Enough time for a neuron to fire hundreds of times. Enough time to die, or fall in love, or miss your train. And this delay is not a bug. It's a feature. It's your brain doing everything it can to create the illusion of a seamless, real-time experience, like editing a live broadcast with a short delay to censor what's not meant to be seen. And if that weren't strange enough, the deception doesn't stop at sight or sound. Even touch, one of the most immediate, visceral sensations you rely on to prove you exist, is subject to this lag. If someone taps your toe and your nose at the same time, your brain receives those signals at different moments, but it edits the timeline. It waits for both signals to arrive, then aligns them to feel simultaneous. You don't live in a stream of reality. You live in an edited documentary of your own life, complete with slow-motion cuts and stitched frames, all curated behind the scenes, milliseconds too late. Now think about this. When you look into someone's eyes and feel present with them, What are you really connecting with? The person standing before you? Or the version of them your brain assembled from echoes and approximations of light and sound and memory? What if the closeness you feel is always with a ghost? A person who's already gone forward, changed, or turned away? The now you believe you share doesn't exist. It's an illusion, like the momentary stillness of a waterfall captured in a photograph. Beautiful, convincing, but utterly false. Philosophers have long questioned the reality of the present. Thinkers like Augustine of Hippo, Henry Bergson, and Immanuel Kant pondered whether now is even a valid concept. Physics answers decisively, it isn't. Einstein's theory of relativity shattered the idea of a universal now. According to relativity, simultaneity is relative. That means what is now for you might be the future for someone else, moving at a different speed or in a different gravitational field. There is no master clock ticking across the cosmos. There is no shared timeline, and without a universal now, our perception of a shared reality crumbles. We are all living in slightly different versions of the past, walking side by side while never actually aligning. And here's the psychological twist. Your self depends on this illusion. You identify with the person you are right now. But if your perception is always behind, then your identity is always lagging too. You are a story you're telling yourself about who you were just a blink ago. Your choices, your beliefs, your reactions, all emerge from a version of you that no longer exists in the present. So, who are you, really? A collection of delayed thoughts? A consciousness echoing through a perceptual delay line? Is free will even meaningful if every decision you make is based on outdated input? This is where neuroscience gets truly unsettling. Consider the Libet experiment, where researchers showed that the brain begins preparing for a decision hundreds of milliseconds before you're consciously aware of making it. Your body knows what it's going to do before you do. Combine that with the delay of perception, and the idea of agency begins to dissolve. You are not driving the car. You are watching the dashboard and assuming you have control, and yet, you still feel real. You still feel here. That's the magic trick. Your consciousness stitches all these fragments into a seamless narrative. It erases the gaps, smooths the cuts, masks the latency. So you can feel whole. So you can feel now, but now is always already over. Even astronomically, the evidence is inescapable. When you gaze at the stars, you are looking into the deep past. The light from Sirius takes 8 years to reach you. From Betelgeuse, over 600 years. From the Andromeda galaxy, 2.5 million years. You have never seen any of them as they are, only as they were. The night sky is a fossilized map, and just like those stars, every moment you perceive, no matter how close, is already gone. So the next time you stop to feel the present, the hum of the world, the breath in your chest, the silence between thoughts, remember this. It's all already history. What you call now is a work of illusion, a brilliant hallucination your brain weaves in the quiet darkness behind your eyes. You are not living in the moment. You are remembering it as it's being written. And yet, strangely, that doesn't make life any less beautiful. In fact, it may make it more so. Because what you experience, this rich, immersive, coherent tapestry of now, is a miracle of cognitive design, a gift of structure layered on top of chaos. The past dressed in present's clothing. Maybe reality doesn't need to be real to be meaningful. Maybe the only thing that matters is what it feels like. And if this delayed illusion can still make you laugh, cry, love, and wonder, then perhaps the past is close enough. Time might not exist at all, according to some theories of quantum gravity. What if time, that invisible thread stretching from birth to death, from cause to effect, from Monday to Friday, wasn't real at all? What if it was nothing, more than a convenient illusion, a conceptual scaffolding your mind builds to make sense of change, but with no actual existence in the fabric of the universe? Imagine trying to explain a melody without referencing time, or trying to feel nostalgia without a past, or anticipation without a future. It sounds absurd, even offensive to common sense, and yet Some of the most advanced, mind-bending theories in physics, particularly those dancing at the edge of quantum gravity, suggest precisely that time might not exist. Not in the way we experience it, not as a flow or a ticking river or a backdrop against which the universe unfolds, but rather as an emergent illusion, a side effect of more fundamental, timeless processes. In this strange view, reality doesn't happen in time. Time happens in reality, and that reversal changes everything. To understand how we got here, how we arrived at the notion that time might not be fundamental, we have to first confront the uneasy marriage between our two greatest physical theories, general relativity and quantum mechanics. Einstein's relativity treats time as flexible, woven into the very fabric of space, stretching and warping under the influence of mass and energy. It explains why clocks tick slower near black holes, why GPS satellites need to correct their time constantly, and why simultaneity is relative. Time in Einstein's hands is dynamic. It bends, but it still exists. In contrast, quantum mechanics, which governs the subatomic world, treats time differently. In most formulations, it assumes time as an unbending, external parameter, a stage on which particles dance, but which itself does not participate. Time, in quantum physics, is absolute, always ticking forward, always in the background. And this is a problem, a big one, because when physicists try to unify these two giants into a single theory of quantum gravity, a framework that explains both black holes and quarks, they find that time disappears from the equations. Take, for example, the Wheeler-DeWitt equation, a candidate for a wave function of the universe, a mathematical attempt to describe the entire cosmos at once. What's shocking about this equation is not just its complexity, but its silence. It has no t, no time variable. It describes a static, timeless universe, a frozen, eternal structure. And in this equation's gaze, the universe doesn't evolve. It simply is. All of history, all of motion, all of becoming is absent. This is sometimes called the problem of time in quantum gravity, because if our most fundamental description of the universe doesn't include time, then what exactly is changing? To visualize this, imagine a DVD of your life. Every frame, from your first breath to your last word, exists all at once, etched in plastic. You, laughing at age 7. You, crying in a breakup. You, sitting here now. They all coexist, not in a line but in a block. There is no now frame playing out. The DVD doesn't care what part is present. It just holds all of it. In this analogy, the flow of time is not something the DVD provides. It's something your DVD player creates. Your consciousness is the player. The passage of time is the illusion it generates while scanning through still images. In physics, this is similar to the block universe view. The idea that past, present, and future all equally exist, and the sensation of flow is a product of our perspective. But if time doesn't exist fundamentally, if it's not a building block of reality, then why does it feel so real? Why do we remember the past but not the future? Why does entropy increase in one direction, not both? The answers are murky, but one hypothesis suggests that time emerges from entanglement. That is, when particles become correlated, when systems interact and exchange information, they gain what we perceive as direction. In such a framework, time is not a pre-existing river. It's more like a shadow cast by relationships, a byproduct of complexity. When the universe was simple, hot, dense, uniform, time didn't exist as we know it. But as the cosmos expanded and diversified, as systems grew entangled and information flowed, a sense of past and future arose. Not as absolutes, but as emergent perspectives. Carlo Rovelli, one of the pioneers of loop quantum gravity, goes even further. He argues that our entire concept of time is built on approximations. We assume that clocks measure time, but clocks don't measure time. They measure change. And change is local. There is no universal now, no master rhythm. Different. Observers experience different orders of events. So what we call time is just a statistical smoothing over of multiple evolving variables. In this sense, time is not a thing. It's a language for describing sequences of change, not a backdrop that causes it. This is a radically disorienting view, because it means that many of the stories we tell ourselves about who we are, how we got here, where we're going, might be built on a false premise. We think of life as a journey, a forward motion through time. We talk about goals, deadlines, progress. We count birthdays, fear aging, chase the future. But if time is not real, then what are we really moving through? What are we measuring? And if past and future are illusions, then perhaps all that truly exists is existence itself. Still, silent, eternal, waiting to be noticed. Of course, none of this cancels the experience of time. The illusion is robust, persistent, and deeply meaningful. In everyday life, time helps you catch buses, fall in love, keep promises, mourn losses. It gives structure to thought. It gives narrative to memory. It gives urgency to purpose. But just as a rainbow is real in your eyes but not in the sky, time may be real in your mind, but absent in the cosmos. You are the projector. Time is the film. Reality is the light beam. So what does it mean to live in a world without time? Perhaps it means that presence, true presence, is not a position in a timeline, but an awakening to timelessness. A recognition that the now isn't fleeting, it's all there is. That underneath the ticking clock, the changing seasons, the grey hairs and worn shoes, there is a kind of stillness, a place beyond, before and after, where the self is not travelling through time, but rather unfolding across layers of potential. You might still check the clock tomorrow. You might still run late or plan ahead. But somewhere inside you, beyond your heartbeat, beneath your breath, you'll know that time is not a river carrying you forward. It is a mirror, curved and cracked, reflecting a timeless you across a stage that never truly changes. The twin paradox. Why time can age people differently. It's a simple story with an impossible outcome. A tale of two siblings, born seconds apart, raised under the same sky, laughing in the same kitchen, and yet doomed by physics to age at different rates, not because of illness, trauma, or luck, but because one of them took a different path through time itself. This is the heart of the twin paradox, a riddle not crafted by philosophers or poets, but by the cold precision of Einstein's theory of special relativity. It begins with a thought experiment so elegant and so unsettling that it forces us to question one of our deepest assumptions, that time is fair, that it ticks the same for all of us, that no matter who we are or where we go, we all march forward at the same pace, 1 second per second. But in the universe revealed by physics, time is not fair. It bends, it stretches, it favors the slow and punishes the fast. And it means that two people, born as twins, can live through vastly different amounts of time, and that one can return to the other decades older, having aged a lifetime while the other stayed young. Imagine two twins. One stays on Earth, grounded, rooted, tied to the gentle tick of local time. The other climbs aboard a spacecraft, capable of moving at an appreciable fraction of the speed of light, let's say 90% or more. From the astronaut twins' point of view, they accelerate, travel far into space, turn around, and return. For them, perhaps only a few years pass. But when they land, they're greeted not by the same sibling they left behind, but by someone who is now decades older. Wrinkles carved by years of sun, hair faded by time, memories accumulated like sediment. They were born together, yet time played favorites. The twin who left and returned has lived less life. And this isn't just theoretical. It's been tested in smaller versions with particles and even actual atomic clocks flown in jets. Time dilation is real, measurable, and irreversible, and it fractures our naive belief in a shared timeline. But how does this happen? To understand the paradox, you must first abandon the comforting notion that time flows independently of space, that it's a river you float down while the landscape of reality remains fixed. In Einstein's universe, time and space are not separate. They are interwoven into a four-dimensional fabric called space-time. The more you move through space, the less you move through time. In other words, velocity doesn't just affect how fast you go, it affects how fast your clock ticks. The faster you move, the slower time moves for you. This is not perception. This is not illusion. It is a physical compression of experience duration. Here's the metaphor that unlocks it. Imagine life as a path across a landscape. You and your twin are hikers. One of you walks a straight, slow trail. The other takes a steep, winding shortcut that involves climbing ridges, descending valleys, dodging obstacles. From a distance, it might seem the second hiker traveled farther, moved more quickly. But when they reunite, the map reveals the truth. The shortcut didn't cover the same terrain in the same way. One used more of space, the other more of time. And because space-time is conserved, what you gain in motion through space, you lose in motion through time. The traveling twins' journey carved more distance, but stole duration. They traded years for kilometers. Still, the paradox arises not from motion alone, but from acceleration and asymmetry. People often ask, if motion is relative, then why? Can't the twin on the spaceship claim that Earth was the one moving away? Shouldn't they each see the other's clock ticking more slowly? It's a fair question, and the answer lies in the moment the traveling twin turns around. Acceleration breaks the symmetry. When you change direction, you change reference frames. The twin on Earth remains in an inertial frame, while the traveler undergoes acceleration, a real, physical force. This shift is what gives the paradox its resolution. The one who turned, who felt G-forces, who braked, who reversed course, is the one who experienced the compression of subjective time. The still twins' journey is linear. The traveler's is a loop, and loops come at a cost. In reality, we've already glimpsed this effect in the Haffel-Keating experiment of 1971, where atomic clocks were flown around the Earth in opposite directions aboard commercial airliners. When compared to clocks that remained on the ground, the results were striking. Those that had moved faster measured less time. The discrepancy was tiny, nanoseconds, but undeniable. Our technologies today must constantly correct for these relativistic shifts. GPS satellites, for instance, tick faster than clocks on Earth due to both their speed and their position in a weaker gravitational field. If uncorrected, their measurements would drift by kilometers every day. In short, our entire global navigation system is built on the acknowledgement that time is not absolute. But beyond clocks and coordinates, the twin paradox unsettles something far deeper: the concept of identity across time. If you and your twin can age at different rates simply by moving differently, then what does it mean to be the same person over time? What is age, if not just biological timekeeping? What happens to the psychological gap when one twin has lived through 30 birthdays and the other through only 5? Are they still twins in any meaningful sense? Or are they now fundamentally different creatures, sculpted by differing amounts of existence? Time, we now see, is not a uniform thread we all pull through. It's a web, and some strands stretch more than others. The implications ripple outward. In principle, if one could travel fast enough, far enough, and return, they could leap forward in time, skipping centuries, millennia. Time travel into the future is real, at least as a one-way trip. The faster you move, the slower you age. If a spacecraft could reach 99.9999% the speed of light, an astronaut aboard could live out a few subjective years, while tens of thousands of Earth years passed. They'd return to a world unrecognizable, a planet evolved without them. And the journey would not involve wormholes or science fiction machinery. Just speed, just motion, just time playing favorites again. But maybe what makes the twin paradox truly haunting isn't the physics, it's the emotional chasm it opens. Imagine leaving your twin behind, knowing full well that you will return to find them old, possibly gone, their children grown, their voice changed. Imagine standing at the edge of the launch platform, knowing that the price of exploration is separation, not by distance, but by time. The paradox becomes a metaphor for all the moments in life when we feel out of sync, when we return to old places and find them changed, when we meet people we once knew and find we've drifted into different timelines. We are all aging differently, not just in motion, but in attention, in memory, in meaning. So the next time you feel the seconds slipping by, remember, time is not fair, not equal, not absolute. It bends around speed, slows under gravity, and moves with a bias that cares nothing for your calendar. In a universe governed by relativity, the only constant is change, and even that arrives late. You and your twin, your friend, your future self. You are all travelers on diverging timelines, curved by choice and circumstance. And perhaps that's what makes reunions so powerful. Not the act of coming back, but the realization that no one was ever standing still. Time slows down the faster you move. They said speed kills, but they never told you it could kill time itself. That the faster you move through the universe, the less of it you receive. That by pressing the pedal of velocity hard enough, you could stretch a second into a minute, a year into a lifetime. Not for the world around you, but for yourself. This is not metaphor. This is not science fiction. This is time dilation, one of the most hauntingly counterintuitive revelations of Einstein's theory of special relativity. It tells us that time, that sacred river we all believe flows at the same pace, is not a river at all. It is a fabric, and when you race across it fast enough, the fabric folds differently around you. Your heartbeat slows compared to others. Your thoughts drift further apart. Your clock, mechanical or biological, ticks more gently. The faster you move, the less time you're allowed to keep. And in that slowing lies a deep philosophical wound. Because if time is relative, then so is aging, experience, and ultimately, life itself. Let's strip away the poetic veil for a moment and look directly at the physics. According to Einstein, space and time are not independent entities. They are woven together into space-time, a flexible four-dimensional stage upon which the universe performs. And when you move through space, you alter how you move through time. If you are at rest, you move forward through time at your maximum rate. But when you move fast, truly fast, approaching the speed of light, your progress through time slows. This isn't just how others perceive you. This is your internal clock, your biological rhythm, your every atom slowing down relative to those standing still. The faster you go, the more the universe grants you a kind of temporal discount, a smaller slice of each second, and it's been tested over and over. In 1971, the Haffel-Keating experiment sent precise atomic clocks aboard commercial jets, flying eastward and westward around the Earth. When compared with a stationary reference clock upon return, the clocks showed measurable time differences. One had lost time. One had gained it. Not millions of years, but nanoseconds, enough to prove that motion affects the very passage of time. Later, particle physicists noticed that fast-moving muons, unstable subatomic particles, survived longer than expected when accelerated, in labs. Not because they resisted decay, but because they were living in slowed time, moving so fast that their internal processes were granted a reprieve. These weren't thought experiments anymore. They were measurements, facts. To grasp how this works, imagine a high-speed train racing across the countryside. Inside sits a traveler holding a flashlight. They points it straight up. From their perspective, the light travels vertically, up and down. But to an outside observer watching the train zoom by, the light doesn't just move up and down. It traces a diagonal zigzag path through space. And since the speed of light is constant for all observers, that light must take longer to reach its destination on the zigzag route. This delay means that, for the outside observer, time inside the train is ticking slower. This is not a trick of optics. It is a structural truth of space-time. Motion alters temporal flow, but perhaps the most shocking consequence of time dilation is its asymmetry. The one who moves fast experiences less time, not more. Think of time as a budget, and velocity as the price you pay. The faster you move, the more expensive time becomes, and so you get less of it. This leads to haunting possibilities. If you could accelerate close enough to the speed of light, You could travel thousands of years into the future in the span of your own lifetime. You would age months. The Earth would age millennia. Your loved ones would vanish into history. Civilizations would rise and fall while you slept. And when you returned, you would be a ghost from the past, walking through the ashes of futures you never lived. The closer you get to the speed of light, the more extreme this effect becomes. But you will never reach light speed itself. That remains a cosmic speed limit. As your velocity increases, your mass increases, and the energy required to keep accelerating approaches infinity. But even at 90% or 99% the speed of light, the impact is dramatic. For every second that ticks on your clock, 10 or 100 or 1,000 may tick elsewhere. Time, it seems, has no loyalty. And here lies the existential blow. If time is relative, then so is identity. Who are you if your lifespan can stretch or shrink depending on how you move? What is experience if its rate of flow is dictated not by your biology, but by your trajectory through space-time? You may think you're aging like everyone else, second by second, but in reality, you're aging according to a path-dependent equation, a formula rooted in motion. Two people born at the same moment can live entirely different durations, not because of choice or fate, but because one walked and the other ran. The story of life becomes less a shared journey and more a set of individual tracks on a curved, shifting landscape. Of course, we don't notice these effects in daily life. Our speeds are low. A car, a train, even a jet barely scratches the surface of relativistic time dilation. But we live in an age where satellites circle the globe, where astronauts orbit the Earth, and where spacecraft slingshot around planets. These tools require relativity to function correctly. A GPS satellite, without relativistic adjustments, would drift out of sync by 10 kilometers per day. Your phone's navigation depends on equations that admit time flows differently up there. The Earth is a relativistic playground, subtle, invisible, but relentless. And what of the philosophical implications? Time dilation reminds us that there is no universal now, that the idea of a shared present is fiction. When you move, you alter your relation to the timeline of the universe. When you accelerate, you break symmetry. You redefine how much time you're allowed to live, not metaphorically, but biologically, neurologically, psychologically. And this means that existence is not measured in seconds, but in frames of reference. You don't just exist in time. You carve it, shape it, consume it differently depending on your speed. Time isn't the river. You are. Perhaps that's the final metaphor to hold on to. If time is a fabric, you are the needle. Each motion, each decision, each journey through space doesn't just displace you geographically. It tears or stretches the very weave of temporal reality. The faster you move, the more the fabric tightens around you, the thinner your experience of duration becomes. You stitch your way across the universe, and in doing so, you warp the very clock that keeps track of your presence. So the next time you feel time slipping by too quickly, ask yourself, compared to what? Time is not a constant. It's a contract, one that space-time rewrites when you decide to move. And perhaps, just perhaps, in the deep physics of motion, we find the ultimate truth. That speed doesn't just change your location, it changes your life. The delayed choice experiment, the future affects the past. Some questions are so unsettling that the only way we dare ask them is in disguise, behind diagrams, equations, and sterile laboratory setups. But strip away the instruments, and you're left staring directly at the absurd. Can the future rewrite the past? Can something you choose to do right now change what already happened seconds, minutes, or even years ago? Most people would answer no without hesitation. Causality, they'd say, flows forward. We make choices, and those choices shape what comes next, not what came before. But in the eerie shadows of quantum mechanics, where particles behave like riddles and observation collapses possibilities into facts, this assumption crumbles. At the center of this collapse is the delayed choice experiment, a mind-bending twist on the classic double-slit setup that seems to say, not only can observation determine reality, it can reach backwards in time to do it. In this realm, your decisions in the present moment might not just shape the future. They might rewrite the very path that led you here. To grasp this, let's revisit one of the most famous experiments in science: the double-slit experiment. Fire particles, photons, electrons, or atoms, at a barrier with two slits. On the other side is a screen that records where they land. If both slits are open and no one observes the path of the particle, you get an interference pattern, a set of bright and dark bands suggesting that each particle behaved like a wave, going through both slits at once, interfering with itself. But if you place detectors to determine which slit the particle passed through, the interference pattern vanishes. The particle behaves like a solid object, choosing a single path. Observation collapses possibility. You don't just witness the behavior, you define it. Reality is not passive. It responds to attention. This alone is disturbing enough. But in the 1970s, John Archibald Wheeler proposed a crueler question. What if we delay the decision to observe until after the particle has already passed the slits, but before it hits the screen? Does the universe already know what we're going to do, or can our present choice change what the particle did in the past? In the delayed choice experiment, the setup is modified so that the decision to observe or not observe the path of the particle is made only after the particle should have already decided whether to act like a wave or a particle. And, astonishingly, the results show that the particle's behavior conforms to the choice made after it passed the slits. If you choose to measure which path it took, it behaves like a particle. If you choose not to, it behaves like a wave. The interference pattern appears, as if it had never made a path decision at all. It's as though the particle's past behavior was undecided until the future observer chose how to look at it. Let's pause here. Let the implications sink in. Your future action determines a particle's past. The timeline is not linear. It's reactive, rewritable. The effect comes after the cause, and yet modifies the cause itself. Time, in this quantum realm, is not a one-way street. It is a conversation where the future whispers back to the past before the ink is dry. The arrow of time, we believed, pointed forward. But here, it loops, swirls, hesitates. What we're seeing is not a trick of measurement. It's a fundamental property of quantum reality. Some physicists interpret this through the lens of retrocausality, the idea that events in the future can affect outcomes in the past. Others take refuge in the many worlds interpretation, where every possible outcome actually occurs in branching universes, and observation merely selects the branch we happen to live in. Still others invoke the transactional interpretation, which suggests that quantum events involve waves moving both forward and backward in time, like a handshake across past and future. But no matter the interpretation, the experiment itself remains unchanged. Our decision in the present seems to determine the behavior of something that should already be in the past. Here's a metaphor. Imagine walking into a museum and seeing two possible exhibits behind curtains. One shows a wave, the other a particle. You flip a coin in your pocket to decide which curtain to open, but only after you've already walked past the doorway where the exhibits were built. And when you pull back the curtain, the entire exhibit behind it has rearranged itself to match your delayed decision, retroactively sculpting history. That is the delayed choice. That is quantum madness. The implications go far beyond particle physics. If observation truly reaches backward, then memory, identity, and experience themselves become suspect. What if your current state, your consciousness, your emotional focus, your intent, is not just a result of past inputs, but a shaper of them? What if your present self is in constant dialogue with your history, not just remembering it, but rewriting it to conform with your evolving understanding? This isn't just philosophical fluff. Neuroscience has shown that every time you recall a memory, you alter it. The past is not a fixed recording. It's a dynamic reconstruction, heavily influenced by your present mood, context, and interpretation. Perhaps quantum physics and consciousness share more than we think. Both create coherence by collapsing ambiguity. Both assign meaning retroactively. Both build narratives from chaos. And this leads us to a chilling possibility. If reality is not fixed until observed, and if observation can reach backward, then what else about our past is uncertain? What if events we believe are done, settled, closed, are still open to revision, waiting for the right kind of attention, the right kind of choice, to finally define them? In this view, the past is not something you move away from. It's something that moves with you, plastic, hovering, undetermined. You don't just travel through time, you sculpt it. But before we descend too far into mysticism, it's important to remember what the data shows. At the quantum level, cause and effect are non-classical. Particles don't behave like tiny billiard balls moving through time. They are probability clouds, and their histories are subject to conditions that exist outside our ordinary temporal framework. The delayed choice experiment doesn't let you send messages to the past or undo tragedies. But it does tell us that the neat story of first this happened, then that, is no longer trustworthy. The universe is not scripted in chronological ink. It is written in erasable graphite, and perhaps this is the paradox we must learn to live with, that while our lives are experienced in sequence, they may be built from loops, that the decisions you make today, even small ones, may resonate backward in subtle ways, reshaping the meaning of what came before. Not because you change the facts, but because you change the frame. A photograph taken years ago looks different after loss. A sentence spoken long ago gains new weight with hindsight. We already rewrite our past emotionally. Physics simply reveals that the structure of reality might allow something eerily similar on a fundamental level. So, what is time, if not a ruler? Perhaps it is a mirror, one that reflects not just what has been, but what could have been, shaped by what is. The delayed choice experiment doesn't just bend the timeline, it bends the mind. It invites you to imagine a universe that is listening, not just to what you've done, but to what you're about to do. A universe where the future is not a destination, but a collaborator. And if that's true, if every choice is a ripple that echoes in both directions, then the responsibility of the present becomes heavier. Because maybe, just maybe, you are not only creating your future, you are completing your past. Black holes. Freeze time from an outside perspective. Not everything that falls disappears. Some things fall forever and never quite arrive. Picture this. A lone astronaut drifts toward the edge of a black hole, arms extended, light shimmering on their visor, and then stillness. From your vantage point, they seem suspended at the event horizon, frozen in time, their final motion never quite completed. No matter how long you watch, they do not move again. It's not a glitch in your vision. It's a glitch in the fabric of space-time itself. Because near a black hole, time doesn't just slow down. It stops. Not for the falling object, but for you, the observer. And in that discrepancy, in that warped difference between what the falling person experiences and what you witness, lies one of the most staggering consequences of general relativity. Gravity can bring time to a halt. From an outside perspective, black holes don't just bend space. They distort time so violently that it breaks down entirely. And the result is a cosmic paradox, where motion continues, yet appears to freeze, where moments pass internally, yet externally seem paused forever. Welcome to the strange theatre of gravity, where the curtain never quite falls. To understand how this happens, we must first accept what Einstein revealed a century ago. Gravity is not a force pulling objects across empty space. It is the curvature of space-time itself. Massive objects like stars, planets, and especially black holes don't emit gravitational pull. They bend the geometry of reality around them. And the more massive and compact the object, the deeper the well it creates in the fabric of existence. A black hole is the ultimate expression of this curvature. A place where the well becomes infinitely deep, where the slope becomes vertical, and no path exists that leads back out. But gravity doesn't just shape space, it alters the very rhythm of time. Clocks tick slower in stronger gravitational fields, and near a black hole, this slowing becomes so extreme that, for a distant observer, a falling object appears to take an infinite amount of time to cross the event horizon. Let's imagine an experiment. You, floating safely in your spacecraft, observe your colleague descending toward the black hole. You're both equipped with synchronized clocks. At first, everything seems normal. You wave, they wave back. They drift closer. But as they approach the event horizon, something changes. Their clock, viewed through your telescope, begins to tick more slowly. The signals they send take longer to arrive. Their gestures become sluggish. Their voice stretches, warps, fades. You call their name, but their reply takes seconds, then minutes, then hours to return. And eventually, they stop responding altogether. Not because they're gone, but because from your perspective, they've become frozen in time, eternally, falling but never reaching. This is not just poetic imagery, it's mathematics. As an object nears the event horizon, the time dilation it experiences, relative to an external observer, becomes so immense that its internal clock effectively grinds to a halt from your point of view. You could orbit the black hole for centuries and still see your friend lingering at the edge, a silent statue of motion. Their fall is real, but your observation of it becomes stretched across eternity. From the perspective of the falling astronaut, however, things are very different. For them, time continues normally. Their clock ticks steadily. Their thoughts flow uninterrupted. They pass the event horizon in finite time, unaware of the optical drama unfolding behind them. But once they cross that threshold, they are cut off forever from the external universe. No message they send can escape. No light, no signal, no story. It's as if they've slipped out of the book of reality, still turning pages, but in a library, no one else can enter. The divide between the internal and external perspectives is complete. What is instantaneous for one becomes eternal for the other. This split is not just unsettling, it's conceptually destabilizing, because it challenges our assumption that time flows uniformly for everyone. We believe that history is a shared chronicle, that moments pass together. But black holes destroy that belief. They create asymmetries in reality itself, dividing it into regions where time behaves in fundamentally incompatible ways. The same event, a body falling toward an event horizon, has two completely different narratives depending on who's watching. One story ends in minutes, the other never ends at all. To make sense of this, physicists rely on Schwarzschild geometry, a solution to Einstein's field equations that describes the spacetime around a non-rotating black hole. In these coordinates, the event horizon is not just a place, it's a boundary of causality. Beyond it, all paths point inward. Even light, traveling at its maximum speed, cannot escape. But more importantly, the equations show that as you approach this boundary from the outside, the time it takes to reach it approaches infinity. And so, for all practical purposes, nothing ever appears to cross it. The surface becomes a kind of cosmic memory, always accumulating, never releasing. An event horizon is not a door, it's a page that never turns. This leads to strange consequences. In theory, a black hole could still be visible for billions of years, not because it's emitting light, but because the light from the objects that fell in long ago is still crawling its way to us, redshifted into oblivion, stretched thinner with every passing second. The image of the person who fell in might still linger, not as a ghost, but as a light echo smeared across time. And this isn't just hypothetical. Astronomers have observed high-energy emissions around black holes that suggest matter falling inward appears to hover near the edge, not because it is held there, but because its collapse is being recorded in slow motion, stretched across space-time like paint across an infinite canvas. And yet, while black holes freeze time from our perspective, they also raise questions about time itself. What does it mean to freeze a moment if the object still experiences time internally? Can two realities, one paused, one progressing, coexist meaningfully? Or are they just mathematical artifacts, illusions born from reference frames that don't communicate? At what point does the distinction between appearance and existence become meaningless? Some physicists argue that black holes are not just physical anomalies, They are windows into the failure of our understanding of time. At their cores, beyond the event horizon, lies the singularity, a point of infinite density and zero volume where the known laws of physics collapse. In that place, space-time doesn't just curve, it tears. And in doing so, it may annihilate our concept of temporal order. Cause and effect dissolve. Sequence breaks down. The universe, as we know it, ends, not in heat or silence, but in the loss of time itself. But perhaps the most powerful metaphor to emerge from this is the idea of frozen tragedy. A loved one lost, a memory suspended, a goodbye never fully said. Black holes, in their cosmic theatre, mirror the emotional experience of grief, a moment that lingers, unreachable, visible but untouchable. We carry echoes of people who are gone, not because they send new messages, but because the light they once gave off is still arriving. The image remains. The presence endures. Time has moved on, but not completely. So the next time you look at the night sky and think of what's out there, remember, somewhere in that darkness, time may be standing still, not for you, but for something you'll never see move again. And maybe, just maybe, that teaches us something about the nature of endings, that sometimes they don't arrive all at once. Sometimes they're frozen at the edge of comprehension, forever falling, never landing. The block universe theory, past, present, and future already exist. Imagine walking into a library where every moment of your life, every thought, every blink, every heartbreak has already been written, bound, and placed on a shelf. You're not writing the story as you go. You're just flipping pages, one by one, through a book that's already complete. You can't skip ahead. You can't go back. But every chapter, from birth to death, is already there, waiting. This is not a metaphor dreamt up by novelists. It's a serious proposal from physics, the block universe theory, also known as the eternalism view of time. In this framework, past, present, and future are not flowing points on a line, but fixed coordinates in a four-dimensional structure. Like cities on a map, they all exist, regardless of whether you're currently visiting them. The sensation of movement through time, of a living now, is not a property of the universe, but a feature of human perception, like a spotlight scanning across a painting that never changes. In the block universe, you aren't traveling through time. You are time. Every version of you, the child, the teenager, the elder, exists eternally, not as memories or expectations, but as unchanging slices of a grand frozen reality. To understand how we arrived at this view, we need to revisit the architecture of space-time as laid out by Einstein's theory of relativity. In Newtonian physics, time was absolute, a universal clock ticking forward at the same rate for everyone, everywhere. But Einstein shattered that assumption. He showed that time and space are inseparable, forming a four-dimensional continuum, where the experience of time depends on one's motion and position. Events that are simultaneous for one observer may not be for another. There is no universal now. This alone cracks open the door to the block universe. If there's no absolute present, then what makes the present special? Why privilege one moment over another when all are equally real from someone's point of view? In this view, the universe is not a film reel that plays forward, one frame at a time. It is the entire reel itself, beginning, middle, and end, existing together, eternally. You, standing at a bus stop in the rain. You, opening your eyes for the first time. You, breathing your last breath. All of those moments coexist, but you only perceive one at a time because your consciousness is moving through the structure, not creating it. Your sensation of flow, of change, is an illusion produced by your brain. Much like how a flipbook appears to animate images when pages are turned rapidly. The story isn't being written, it's being read. The block universe is mathematically elegant, but emotionally jarring. It undermines the very foundation of how we think about time, choice, and identity. If all moments exist eternally, then so do all decisions. Your triumphs and failures, your regrets and achievements, none of them were ever open-ended. They are coordinates in a timeless grid. You didn't choose them in a linear sense. You simply occupy the points in space-time where they occur. This doesn't mean you are a puppet. It means that free will must be reinterpreted. Rather than choosing between possible futures, perhaps you are expressing a pre-existing self across the dimension of time. Your choices feel free because you are the conscious experience of the path you take, not the author of that path, but its witness. There's also a deeper consequence. The future already exists, not in a vague potential sense, but concretely, structurally. Somewhere in the block universe, the version of you reading this sentence is a static coordinate, and so is the version of you who will one day remember having read it. They both exist. You just haven't experienced the second one yet. The future you isn't waiting to be born. It's already written, already carved into the geometry of space-time. And this means something even more haunting. Nothing is ever truly gone. Everyone you've lost, everything you've loved, it still exists in its own slice of the block. You've simply moved to a different page. You can't turn back, but the page doesn't vanish. In that structure, nothing dies. It just stops being part of your current cross-section. Some find comfort in this, others recoil in horror. Because if this theory is true, then change is not fundamental. It's apparent. The world doesn't evolve. It simply is, eternally. The Big Bang, the first star, the first cell dividing, your first kiss, they are all just parts of a fixed four-dimensional sculpture, and your mind is the sculptor's eye, tracing a path through it. This static view of time is difficult to reconcile with our experience of motion, emotion, evolution. We feel growth. We feel anticipation. We hope, plan, grieve. These are not illusions in the trivial sense. They are deeply encoded in the biological machinery of human consciousness. But physics suggests that they are not properties of the universe itself, only of the beings who inhabit it. And yet, the block universe isn't just a cold abstraction. It carries strange beauty. If every moment exists forever, then so does every act of kindness, every connection, every breathless, fragile second of intimacy. They are not swallowed by entropy. They are preserved in the structure of reality itself. You may not be able to revisit them, but they are never erased. They are part of the cosmic architecture, as real as any star or planet. Every goodbye you ever whispered still echoes in its own corner of space-time. Every laugh still rings out somewhere along your world line. But what about change? What about becoming? If everything already exists, what's the point of anything? This is where the block universe challenges not just our physics, but our philosophy. It tells us that life is not a journey of transformation, but an unfolding of presence. That growth is not a movement, but a map. You don't become someone. You are already everyone you've ever been. The child, the parent, the stranger, the friend, all existing simultaneously, eternally, side by side in the block. You are not a flame burning across time. You are a constellation, a shape drawn across space-time, visible only from the outside. The present is not the tip of an arrow. It's just one star in that constellation, and still, in spite of all this, we live. We feel time move. We race it, curse it, treasure it. We wake and sleep, grow old and die, make promises and break them. Even if physics says this flow is an illusion, it remains the most powerful story we know. The story of becoming, the story of change. And maybe that's what matters most. That even in a frozen universe, meaning can still melt from one moment into the next, through the act of experiencing it. So if the block universe is true, if the past and future are as real as the present, then perhaps we owe it to ourselves to treat each moment with reverence, not as something fleeting, but as something permanent, something engraved. The love you give today will always be given. The forgiveness you offer will always echo. The time you waste will always remain wasted. and the time you cherish will always exist, somewhere, forever, glowing. Entropy defines time's arrow, but physics doesn't prefer a direction. There's something strangely comforting in the belief that time moves forward, that shattered glasses never reassemble, that smoke doesn't drift back into a match, that childhood leads to adulthood and not the other way around. We rely on this direction, this one-way street of time, to make sense of everything. But what if that comforting sense of direction isn't a property of the universe, but a quirk of disorder? What if the arrow of time, that unstoppable flow from past to future, doesn't arise from the laws of physics, but from a statistical tendency for things to unravel, decay, and scatter? At the deepest level, the equations of physics don't care what direction time flows in. They work just as well backward as forward. The only reason we see time marching ahead is because entropy increases. And if that's true, then everything we associate with time, memory, cause, loss, identity, might not be anchored in the structure of reality, but in the tendency of systems to drift from order to chaos. Time, in this view, is not a force, but a symptom, not a flow, but a stain. Let's start at the core of this concept, entropy. In thermodynamics, entropy is often described as a measure of disorder, or more precisely, the number of possible microscopic configurations a system can have. A neatly stacked deck of cards has low entropy, a shuffled one, high. A new house has low entropy, a collapsed ruin, high. A hot cup of coffee cooling in a room distributes its heat, not because it wants to, but because there are more ways for the molecules to be evenly spread than tightly organized. And therein lies the key. Systems evolve from low probability states to high probability states, from neatness to messiness, simply because messiness has more possible arrangements. Entropy increases because there are more ways to be disordered than ordered. And as entropy increases, we mark that as the passage of time. But entropy doesn't force time forward. It just correlates with what we call later. It defines the direction in which memory accumulates, where cause precedes effect, and where decay replaces growth. But the equations underneath, Newton's laws, Maxwell's equations, even the quantum formalism of Schrödinger's equation, are time symmetric. They don't distinguish between past and future. If you filmed a collision of two particles and played it backward, the math would still hold. A pendulum swinging obeys the same rules in reverse. The orbit of planets, the bouncing of balls, the dance of atoms, all are blind to the direction of time. So where does the arrow come from? The answer, disturbingly, is initial conditions. The reason we experience time flowing from past to future is because the universe started in a state of incredibly low entropy, a smooth, hot, homogeneous soup at the moment of the Big Bang. Since then, entropy has been rising, not because it must, but because that's what's statistically likely. In other words, the arrow of time is born not in law, but in luck. The universe didn't have to start ordered, but it did. And because of that, we move from less probable to more probable configurations, from youth to age, from clarity to forgetfulness, from birth to death. Here's a metaphor. Imagine a pristine sandcastle built on the beach. With time, wind, and waves wear it down into formless sand. That's entropy at work. Not because the sand wants to be disordered, but because there are millions more ways for sand to be scattered than for it to be sculpted. Now imagine watching that process in reverse. The sand grains leap together, arrange into towers and arches. That reversal is possible in theory. Nothing in physics forbids it, but it's so statistically unlikely that it becomes functionally impossible. That's what time is. The direction from improbable to probable. We experience the build-up of entropy as forward motion. But underneath, it's all just shifting statistics. And what about memory? Why do we remember the past, but not the future? Because memory is a low entropy encoding of a high entropy environment. Your brain forms patterns. It sculpts a representation of events that have already happened, moments when entropy was lower than it is now. You can't remember the future because those lower entropy configurations haven't been accessed, yet by your conscious thread of experience. But in the block universe, where all times coexist, The future is already written. Your inability to perceive it isn't a statement about its reality, but about your position in the entropic gradient. You are a creature born from the rise of disorder, and you interpret increasing entropy as passage through time. Your brain is not just a memory machine, it is an entropy navigator, tracing a path through the irreversible. And here's the kicker. If the laws of physics are indifferent to direction, and if entropy defines our perception of time's flow, then we live in a universe where there is no objective forward. The future isn't more real than the past. It's just more forgotten. The only thing distinguishing yesterday from tomorrow is the arrangement of particles, the organization of information. When a cup shatters, you call it progress. When it reassembles, you call it impossible. But to the universe, both are just configurations. The only difference is statistical. Time is a bias of memory, a preference for lower entropy to precede higher. But it didn't have to be that way. Flip the initial conditions, and we might have remembered tomorrow and feared yesterday. Some physicists, like Sean Carroll, suggest that the reason entropy increases is because the early universe was so improbably ordered that it left vast room for disorder to grow. That room is what we call time. We move forward through time only because the universe hasn't yet run out of ways to become more chaotic. When entropy reaches its maximum, when every atom has settled into its most probable configuration, what's known as heat death, time as we know it, may cease to exist. Not because clocks will stop, but because nothing new will happen. No more gradients, no more memory, no more change, just endless stasis, a silence not of sound, but of events, a timeless now that never ends. And so we return to the arrow. It feels so intrinsic, so sacred, but it's built on fragile foundations. A statistical fluke at the beginning of time, a one-time roll of the cosmic dice. Our entire sense of becoming, of moving through life, is tied to how particles spread out, how warmth dissolves, how structures collapse. Every heartbreak, every death, every moment of aging, these are symptoms of entropy. But so is growth, so is love, so is memory. In a strange twist, everything that matters arises not in spite of entropy, but because of it. Without it, there would be no arrow, no time, no self. You would not be reading this, nor wondering about what comes next. So what then is time? Not a ticking metronome, not a thread unwinding, but a gradient of disorder, sloping from improbable birth toward inevitable decay. It's a one-way trip we feel only because the universe began with all its pieces neatly arranged, and now they're tumbling, dancing, falling apart. And in that fall, we find meaning. Not because the future is more real than the past, but because we are always in the middle of a cascade. Surfing entropy's wave, eyes forward, hearts wondering what comes next. Time reversal symmetry. Equations work. Both ways, so why don't we? Imagine waking up one morning to find that everything is playing in reverse. Raindrops leap upward into clouds. Broken vases reassemble with elegance. Laughter rewinds into silence, and people walk backward into rooms they had just exited. It would feel wrong, unnatural, like watching life through a mirror bent in time. And yet, if the laws of physics were the only things that mattered, if the universe obeyed only its core mathematical principles, this reversed reality would be just as valid as the one you live in now. The fundamental equations that govern our universe, from Newton's motion laws to Maxwell's electromagnetism, from Schrödinger's wave functions to Feynman's path integrals, are all time reversal symmetric. They do not care whether time flows forward or backward. They function identically in both directions. So here's the paradox. If the universe's rulebook plays no favorites, why do we? Why do eggs crack but never uncrack? Why does smoke drift away from fire but never return? Why do we remember the past but never the future, even though the math treats both equally? Somewhere between the equations and the experience, something breaks the symmetry. And in that fracture lies the mystery of time. Let's begin with the raw mathematics. If you take Newton's second law, force equals mass times acceleration, and reverse the direction of time, the equation still holds. The acceleration becomes negative, but the law remains valid. Likewise, Maxwell's equations, which describe how electric and magnetic fields evolve, are invariant under time reversal. The direction of a wave can flip, but the form of the field persists. Even quantum mechanics, with all its weirdness, doesn't inherently require a forward arrow. Schrödinger's equation, the cornerstone of quantum theory, is completely reversible. If you reverse the wave function in time, the equation still works. So why does reality appear to have a preference? Why is there a before and an after, a was and a will be, when the underlying machinery makes no such distinction? One common answer is entropy, the statistical measure of disorder. As we saw in the previous chapter, entropy tends to increase over time, giving rise to the psychological and thermodynamic arrow of time. A broken vase has more possible configurations than an intact one. So the journey from whole to shattered is statistically inevitable, while the reverse is astronomically unlikely. But entropy explains why we see time flow in one direction, not why the laws themselves allow both. Entropy arises from boundary conditions, from the fact that the universe began in a low entropy state. The laws still don't care. They provide the stage. The script, the forward-pointing narrative we experience, is written by the way energy, matter, and initial states arrange themselves, which means the asymmetry we live inside is not built into the rules. It's built into the context. Here's a metaphor. Imagine a perfectly symmetrical seesaw balanced at its center. The physics of the Planck, the fulcrum, the force, all are symmetric. But place a single pebble on one side, and it tilts. The rules haven't changed. The initial condition has. Time, too, may be that seesaw. The laws are symmetrical, but the pebble, the Big Bang's improbable order, tipped it, and now we all slide down in one direction, mistaking momentum for inevitability. This raises fascinating consequences. If the equations are time-symmetric, then in principle, the universe could run backward and no law would be broken. The trajectories of every particle could be reversed. The expansion of galaxies contracting. Your death unfolding into youth. Memories forming before events occur. This isn't just philosophical whimsy. In theoretical physics, anti-time universes are considered seriously. Some cosmologists speculate that the universe may be part of a mirror system, where time flows in the opposite direction on the other side of the Big Bang. From our perspective, it's a second universe evolving into our past, but from its own internal viewpoint, it flows forward just like ours. Two arrows of time, born from the same singularity, diverging outward in symmetry. Even in quantum field theory, particles have antiparticles, and Feynman himself proposed that a positron, the antimatter equivalent of an electron, can be thought of as an electron traveling backward in time. In Feynman diagrams, this isn't just poetic, it's mathematically meaningful. In that interpretation, every interaction of matter and antimatter is a dialogue across temporal directions. So, in some formulations, we are constantly interacting with time-reversed versions of the world, and yet we remain unaware, because our conscious experience is trapped inside one direction of entropy. But then the question sharpens. If physics allows reversal, why don't we ever see it? Why can't we observe a shattered glass reassembling itself in slow, graceful defiance of disorder? The answer lies not in impossibility, but in improbability. Such events are permitted, but they are so statistically rare that they may as well be impossible. The universe could allow a hurricane to sweep through a junkyard and assemble a Boeing 747, but the number of required coincidences makes it cosmically absurd. And so, the symmetry of physics remains buried beneath a sea of chaotic statistics. The laws allow, but the odds deny. This tension between reversible laws and irreversible experience isn't just a puzzle, it's a window into something profound. Time, as we experience it, is emergent. It arises from layers of interaction, from systems of particles exchanging energy and information in irreversible ways. But beneath those layers, in the silent depths of equations, time is an illusion, or at least a choice. Nature can be played backward, like a film, and the frames would still make mathematical sense. The story would feel wrong, but only to us. This opens up a philosophical wound. If the fundamental laws don't distinguish between past and future, then what makes us so sure that time flows at all? Maybe flow is a mental construct, a spotlight passing over a static landscape, lighting up one moment after another, giving the illusion of motion. Maybe the self is not a traveler, but a sequence of snapshots arranged in a particular order. And if that's true, then the difference between your birth and your death is not a journey, but a juxtaposition of frames that feel linear only from the inside. So what are we left with? A universe whose deepest truths refuse to anchor us in one direction. A reality where every forward step is mirrored by a possible backward one, hidden in the math, but absent from our senses. And in that absence lies the drama of time. We are creatures born in entropy, sculpted by asymmetry, and addicted to the illusion of forwardness. We define meaning through progress, loss, hope, aging, none of which exist in the math, but all of which rule our hearts. So the next time you drop a glass, or forget a name, or watch a sunset vanish into memory, remember, the equations didn't make it happen that way. They were indifferent. Time could have flowed the other way, and the math wouldn't blink. The universe didn't choose a direction. We just happened to wake up on one side of the mirror. Simultaneity is an illusion. What happens now depends on where you are. There's a kind of magic in believing that we all share the same now. That as you sit and listen, someone across the world is breathing in sync with you, thinking, their thoughts, living their life, all in the same moment. It gives us the illusion of unity, of shared reality, of a global heartbeat pulsing through all things at once. But the truth, whispered quietly through the equations of Einstein's relativity, is far more alien. There is no such thing as universal now. There is no single moment that spans the cosmos and binds all observers into the same present. What's happening now for you is not what's happening now for someone moving past you or standing far away from you. Simultaneity is not objective. It is personal, relative, and shockingly fragile. And once you understand that, you begin to see that our most basic assumptions about time, presence, and connection are built not on reality, but on convenience. 2. Grasp the scale of this illusion. Imagine two lightning bolts striking a railroad track, one at the front of a train, one at the back. If you're standing on the platform, equidistant from both strikes, you see them happen at the same time. To you, they are simultaneous. But now imagine a passenger riding inside the train, moving forward, because the train is moving toward the strike at the front and away from the one at the back. The light from the front strike reaches them before the light from the back. So from the passenger's perspective, the strikes were not simultaneous. And here's the twist. Both observers are correct. Neither is wrong. Each is reporting what they measure from their own frame of reference. And in Einstein's universe, both realities are equally valid. This is not just a trick of perception, it's a fundamental truth of space-time. The theory of special relativity teaches us that time and space are linked, and that motion through space alters how you perceive time. Different observers, moving at different speeds, or located in different places, will slice up space-time differently. They will disagree about what events happen at the same time. This means that now is not a shared horizon. It's a local phenomenon, limited to your particular frame. And this leads to the strange but inescapable conclusion that what's happening now for you might be in someone else's past or future. Let's take this further. Imagine two people drifting in space, miles apart. One is stationary, the other is moving rapidly past. In their respective frames of reference, the order of distant events can flip. A star exploding in a galaxy millions of light years away might happen before a spacecraft launches from Earth in one frame, but after it in another. The timing of events that are far apart in space becomes malleable, negotiable, subject to the observer's motion. There is no global clock keeping synchronized time for the universe. Each point in space, each observer, carries their own version of time, like a watch that runs independently of all others. Here's a metaphor. Imagine space-time as a massive loaf of bread, with each slice representing a now. Depending on how you move through the loaf, how fast you go, and in what direction, your slice will tilt. It won't be horizontal. It won't align with anyone else's. Your now cuts through different parts of the loaf than someone else's. This idea, called the relativity of simultaneity, is not just theoretical. It is embedded in the geometry of the universe. There is no cosmic stage where everyone is acting in sync. Each actor is reading their script from a slightly different page. You may ask, if simultaneity is an illusion, how do we function? How do we make phone calls, conduct meetings, synchronize data? The answer is that on Earth, at human speeds and distances, the effects of relativistic simultaneity are so tiny that we can ignore them without consequence. But at higher speeds, or across cosmic distances, the illusion breaks. Satellites in orbit already experience time differently than we do on Earth, requiring corrections to stay in sync. If we ever travel at near-light speeds or communicate with civilizations across the galaxy, we'll have to abandon the notion that we share a common now, because in truth, we never did, and this has emotional consequences, not just physical ones. We imagine ourselves as living together in time, families eating dinner, lovers watching sunsets on opposite shores, explorers landing on distant worlds at the same moment. But physics tells us that such shared moments don't exist in any absolute sense. They are creations of proximity and approximation. The person you love across the world is not experiencing the same now as you. They never were. Your clocks may match, but your frames of reference do not. You are always slightly out of sync, even with those closest to you. And yet, we continue to reach for each other, to hold on to this illusion of simultaneity, because it makes connection feel real. This brings us to a deeper truth. Perhaps it doesn't matter that simultaneity is an illusion. Perhaps it's a necessary illusion, a psychological scaffold that allows us to build meaning. When you call someone and say, "Right now, I'm thinking of you," what you mean is not that your moments align perfectly in a relativistic sense, but that your minds are directed toward each other. Your attention is synchronized, even if your clocks are not. Connection isn't about simultaneity, it's about intent. Still, the physics remains, and it humbles us. It tells us that now is not universal, that the cosmos doesn't move in one rhythm, but in countless overlapping melodies, none of them in perfect harmony. It tells us that time is local, perspective-based, fragile, that what feels solid and shared is, in fact, fragmented and floating. But perhaps that fragmentation is what makes existence so richly complex. Perhaps the lack of a single now is what gives rise to the beautiful variety of experiences, stories, memories, each unfolding on its own slice of space-time. So, the next time you check the time, or speak of what's happening right now, remember that now is yours alone, a private horizon, a sliver of the universe that only you can see, and everyone else, the people you love, the people you've lost, the strangers drifting through their own orbits. They're living in their own shimmering versions of now, each slightly skewed, each slightly out of phase. We are not passengers on the same train. We are stars in different constellations, visible from different angles, shining at slightly different times. And yet, somehow, we still manage to find each other. You never experience the present, only a mental reconstruction. There is a strange kind of betrayal at the core of your consciousness, one so subtle, so persistent, that you never even notice it. You have never truly lived in the present, not once, not for a second, not even in the most heightened states of awareness, not during the most vivid sensations, not when staring into the eyes of someone you love or feeling the sting of pain. What you think of as now is already gone by the time you perceive it. The moment you believe you're living is in truth already in the past. Your brain, ever the silent editor, constantly delays, reconstructs, and fabricates what you experience, delivering not the world as it is, but the world as it was, carefully arranged and presented to feel seamless. Your reality is not a live broadcast. It is a heavily edited replay. And once you see through that illusion, Once you truly grasp that your experience is always lagging behind existence, it reshapes everything: memory, identity, decision, even the nature of self-awareness. Let's begin with what neuroscience tells us, plainly and disturbingly. When sensory data enters your body, whether it's photons hitting your retinas, sound waves vibrating your eardrums, or pressure against your skin, it does not instantly become perception. It must first be translated into electrical signals, routed through the nervous system, processed by multiple brain regions, integrated with existing knowledge, and only then elevated into consciousness. This takes time. Not much, mere milliseconds, but enough to sever your experience from the immediacy of the world. Studies suggest your brain takes 80 to 100 milliseconds to construct what you believe is the present moment. That doesn't sound like much, until you realize that in that gap, a fly can flap its wings dozens of times. A neuron can fire hundreds of signals. A speeding car can travel several feet. The delay is enough to make everything you see, feel, and know a reconstruction, not a direct connection. But the brain doesn't just present delayed information, it actively edits and synchronizes it. If sound and light arrive at different times, as they often do, the brain waits to synchronize them before delivering them to you as a single, unified event. When someone claps their hands at a distance, light reaches you before the sound, but your brain aligns them so you perceive them as simultaneous. This means your now isn't a continuous stream, but a stitched-together illusion, held together by neurological guesswork and statistical prediction. Your brain discards the raw footage of reality and gives you the version that makes sense, the one that won't confuse or disorient you. Consider the phenomenon of the postdictive effect. In certain rapid visual experiments, participants report seeing events that, from a physical standpoint, hadn't occurred yet at the moment they claim to experience them. It's as if the brain waits to collect more data before finalizing what it says happened just now. Your perception of the present, in other words, is partially determined by the future, not of the world, but of your nervous system. The brain samples input, delays output, then constructs a story that feels immediate. It's like reading the last paragraph of a chapter and realizing it's been edited to match the twist that came after the scene ended. This mental time lag isn't just sensory, it reaches into your sense of agency. Consider the readiness potential in neuroscience, the brain activity that builds before you make a conscious decision to act. Experiments show that your brain begins preparing for voluntary movement hundreds of milliseconds before you become aware of wanting to move. When you decide to raise your hand, your brain already made the choice. Your conscious experience is a narrative overlay, a story your mind tells itself to explain actions that already started. And if your decisions are based on lagging data and post hoc rationalization, then who is really acting in the moment? Who were you, if not a reconstructed character, in your own play? This brings us to the psychological present, the concept that what we perceive as now isn't an instant, but a short temporal window. Studies in cognitive science show that we experience now as a window approximately 3 seconds long, within which we integrate stimuli, form impressions, and update memory. Your brain treats everything that happens in that span as part of a single moment, like a mental shutter speed. That's why music feels rhythmic, conversation flows, and actions feel coordinated. But it also means your perception is not a point on the timeline. It's a blurred region, a flexible bracket around delayed input. The present you think you're living is a guess, not a given. Here's a metaphor. Imagine walking through a museum at night with only a flashlight. The beam lights up sections of the room, but there's always a slight delay between what you see and where you actually are. You never see the present room, only its immediate past, already stepped through. And yet, the experience feels fluid, because your brain adjusts the timing, smooths the transitions, and fills in the gaps. You're not moving through time. You're moving through a reconstruction of time, sculpted by attention and prediction, and the consequences ripple outward. Memory itself is not immune. Every time you recall a moment, your brain partially rewrites it. The act of remembering is not like opening a file, it's like repainting a canvas. And because your present perception is already a reconstruction, Your memories are reconstructions of reconstructions. You are a story built on stories, none of which were ever truly live. This doesn't mean your life is a lie. It means your life is a narrative, one continuously revised to maintain coherence, not accuracy. Philosophers have long suspected this. St. Augustine once wrote, "What then is time? If no one asks me, I know. If I wish to explain it, I do not." The mystifying nature of the present haunted thinkers from Kant to Bergson, all grappling with the idea that the now is both undeniable and elusive. And neuroscience has now caught up, showing us that our reality is a simulation. We run on delayed input, one that values stability over precision, flow over fact. So what do we make of this? That the present is fake? That we're just ghosts catching up to where we already were? Not quite. What it really means is that experience is not raw data. It's a masterpiece of integration. Your brain isn't lying to you. It's protecting you from fragmentation. The real world, unfiltered, would be disjointed, desynchronized, overwhelming. Instead, your mind offers you a gift, a smooth, believable present, woven from latency and light. And maybe that's what it means to be conscious, not to live in the moment, but to constantly rebuild it, to patch together fragments into something meaningful. You're not behind reality, you're above it, interpreting it, giving it coherence. The world doesn't offer itself to you directly. You assemble it, always slightly too late, but just in time to believe it's real. The illusion of continuity. Reality is a mental stitching of moments. Blink. Just once. In that fraction of a second, your eyes shut out the world. Light stops flowing to your retinas. Your brain receives no fresh data. And yet you experience no interruption. You don't feel as if existence paused or the universe skipped a frame. Everything feels smooth, continuous, fluid. But that, right there, is the trick. You think you're living in a seamless stream of reality, that life flows like a river. But what you're actually experiencing is more like a slideshow, frame by frame, moment by moment, stitched together not by time, but by the architecture of your mind. Beneath the illusion of flow lies the truth. Continuity is a construction. Your brain takes snapshots of sensation, memory, expectation, and narrative, and weaves them into a coherent experience that feels unbroken. But in reality, you are always leaping, never flowing. And it is your consciousness that fills in the gaps. To grasp how deep this illusion runs, consider what happens in saccadic masking, the brain's ability to hide the momentary blindness caused by rapid eye movements. Each time your eyes dart from one object to another, you go temporarily blind. The visual input becomes a blur, yet your brain erases this disruption and fills in the blank with what it expects to see. You are not seeing the world in real time. You're seeing what your brain predicts and patches together, presenting a fabricated smoothness in place of the jagged and stuttering raw input. And this isn't just a visual phenomenon. It happens across all sensory modalities. What you feel, hear, remember, and think is continuously interpolated, revised, and rearranged into a plausible flow. You're not in a river. You're on a tightrope, with your mind constantly laying the rope down just ahead of your feet. This becomes even more evident when we explore how time is processed in the brain. Cognitive scientists often refer to the temporal binding window, a period of a few hundred milliseconds during which your brain merges stimuli from different sources into a single experience. Sound, sight, and touch arriving within this narrow window are glued together into what you perceive as a single moment. But this glue has a strange consequence. Events that happen at slightly different times are perceived as happening together, while others that are simultaneous but processed differently may appear out of sync. Your sense of now is not instantaneous. It's a mental average, a center of gravity calculated from scattered fragments of sensation. Even your sense of motion, of objects sliding across your vision, of people walking through rooms, of yourself moving through space, is a guess. Motion is not directly perceived, it is inferred. The brain receives discrete images at intervals and computes velocity, direction, and continuity. Just like a movie made of still frames looks fluid when played fast enough, your perception is an animation, not a stream. The world doesn't move. Your mind makes it move. And when this stitching process fails, the illusion shatters. People with certain neurological conditions, like achinotopsia, lose the ability to perceive motion. They see the world as a series of still images, jumping from position to position. When they cross the street, a car doesn't approach. It teleports closer. For them, the brain's stitching mechanism is broken, and it reveals that what we call reality is not out there, flowing independently of us. It's something constructed inside our heads, a kind of cinematic hallucination rendered on the fly. But it's not just perception. Memory plays the same game. Your life feels like a continuous story, but that story is rewritten every time you recall it. What you remember is not what happened, it's what you last remembered. Your identity feels like a single thread, but in truth, it's a quilt. Patches of remembered events, feelings, intentions, and interpretations, sewn together with a thread of narrative. The continuity of self is no more real than the continuity of motion. Both are mental models, built to provide coherence in a world that doesn't offer it naturally. The brain does this not to deceive you, but to protect you. A discontinuous experience of reality would be unbearable. Imagine if every blink felt like a power outage. If every thought arrived with a subtitle saying, "This is probably how things fit together." You would freeze, unable to act, decide, or relate. So the brain fills in the blanks, smooths the transitions, creates the illusion of a world that unfolds steadily. It's not just about what's outside you, it's about keeping what's inside you sane. This brings us to an uncomfortable truth. There may be no continuous experience at all, only discrete moments, stitched by memory and expectation. The philosopher Daniel Dennett has suggested that consciousness may not be a stream, but a narrative engine, continuously building explanations after the fact. What we think of as the present is a draft, constantly edited and re-edited, with no central moment that is fully, cleanly, now. You never arrive in the present. You only reconstruct it from fragments that have already passed. And if this is true, if your reality is a chain of still frames cleverly joined, then what happens to responsibility, to intention, to choice? If you are constantly catching up, always believing the frame you're in is the real one, what does it mean to be decisive? The answer may lie in understanding that agency is not about acting in the moment, but about shaping the story that connects your moments. You are not a point in time. You are the weaver of time's illusion. This also explains why trauma distorts memory, why déjà vu feels like time collapsing in on itself, why boredom makes seconds feel like hours, and fear compresses minutes into blinks. Your brain doesn't measure time. It constructs it, and the feeling of flow or fracture, of rhythm or rupture, comes not from the world, but from how well the stitching holds. So what are you really? Not a continuous being, but a collection of mental snapshots, narratively bound. A ghost in a slideshow, mistaking motion for meaning. But this isn't bleak, it's beautiful, because it means every moment you feel, no matter how fleeting, is a miracle of synthesis, a triumph of coherence over chaos. And maybe, just maybe, the magic of being alive is not in the passage of time, but in the stitching itself, in the way your mind takes broken fragments and turns them into a life that feels like a song. Quantum tunneling. Particles ignore classical time rules. Imagine a locked door, solid, heavy, unbreakable. Behind it, a room you're not supposed to enter. In the classical world, the one you and I move through, you'd need a key, a passcode, or a battering ram. Rules are rules. Boundaries are boundaries. But in the quantum world, particles don't knock. They don't ask permission. They vanish from one side of a barrier and appear on the other, as if the obstacle wasn't there at all. It's not a metaphor. It's not magic. It's quantum tunneling. A real, measurable phenomenon, where particles behave as if time and space don't fully apply to them. They ignore the classical rules that define your every movement, and in doing so, they whisper something radical. That reality is not a rigid structure, but a probability field. That the impossible is sometimes not only possible, it's routine. And once you understand this, it doesn't just change how you see atoms. It changes how you understand causality, presence, time itself, revealing that even the bedrock laws of motion, the ones Newton carved into the intellectual spine of Western science, are only approximations. The quantum world doesn't rewrite reality. It reveals that reality was never what we thought. Let's start with how absurd this sounds through classical eyes. If a ball doesn't have enough energy to roll over a hill, it stops. Always. That's the rule. It's not just intuition, it's thermodynamics, it's conservation of energy, it's logic. But quantum particles, electrons, protons, atoms, even entire molecules, play by different rules. According to quantum mechanics, a particle doesn't exist at a single point. It exists as a probability cloud, a wave function that describes all the places it could possibly be. And when that cloud brushes against a barrier, something strange happens. Even if it doesn't have enough energy to climb the barrier, there's still a non-zero probability that part of it exists on the other side. The universe, quite literally, allows for miracles, not often, not reliably, but statistically. That's all the universe needs. And when we measure it, we don't see a particle struggle and fail, try and try again. We see a particle that simply wasn't here. And now it is, like a ghost stepping through a wall, like a thought jumping over silence. This phenomenon isn't rare. It happens constantly, and you are alive because of it. In the heart of the sun, quantum tunneling is the reason fusion happens at all. Protons in the core of the sun, with their mutual positive charges, repel each other fiercely. According to classical physics, they should never get close enough to fuse. But quantum tunneling gives them a shortcut. It allows them to skip the classical energy barrier and merge despite the odds, igniting the chain reactions that produce light, heat, and ultimately, life. Without quantum tunneling, the sun would be a cold, lifeless ball of gas. The Faraday trees, the oceans, your thoughts, none of it would exist. The laws of the small allow the large to survive, and they do it by cheating. But what does it mean for time? For movement? For causality? Tunneling is not just weird spatially, it's weird temporally. When we try to measure how long a particle spends inside the forbidden zone, that space inside the barrier, the numbers get slippery. Some experiments suggest zero time. Others suggest imaginary time. Not metaphorically imaginary, but literally involving the square root of -1. That is, time becomes a complex number in the equations. It no longer flows. It warps. It folds. And if time doesn't behave during tunneling, then what is a moment? When does a particle decide to tunnel? Does it even decide? Or is this motionless motion, movement without travel, a glimpse into a reality where becoming matters more than being? This defiance of time has deep implications. In 1993, physicist Günther Nimtz claimed that under certain tunneling conditions, signals appeared to travel faster than light, violating Einstein's cosmic speed limit. Though later refined and debated, the experiment raised a haunting question. Are particles communicating outside time? Are they tapping into a realm where sequence collapses, where before and after blur, where potential shortcuts in the quantum foam bypass the linear story we live by? It's not just science fiction, it's testable, mathematical physics. And though the consensus today is that tunneling doesn't break causality, it undeniably bends it. In the quantum world, causality is fuzzy, not fixed, and that fuzziness ripples outward. Think of the scanning tunneling microscope, a device that images surfaces at the atomic level by relying on electrons tunneling across a gap. It's not only proof that tunneling happens, it's a tool built on it. We've engineered technology around what should be impossible, proof that our entire macro world rests on quantum foundations that openly violate classical logic. And yet we trust bridges, airplanes, medicine. The irony is beautiful. The most stable systems we rely on are built on the most unstable foundations we can imagine. Still, it's hard to wrap the human mind around it. We live in a world of doors, barriers, limits. A reality of this or that, of causes and effects. We don't feel quantum probabilities. We feel weight, resistance, time. But at the subatomic scale, those sensations collapse into math. Reality isn't a sequence of events. It's a field of possibilities. And tunneling is the moment when a particle slips between possibilities. Not over, not through, between. And once you realize this, it infects how you see everything else. The idea that a particle can teleport without traveling, can pass through a wall without touching it, can obey rules we don't understand. It shakes the foundation of certainty. It suggests that boundaries, both physical and mental, are softer than they appear. What if thought itself tunnels? What if the sudden insights you get, those lightning flash moments of clarity or intuition, aren't linear conclusions, but mental tunneling events? What if, beneath the structure of your conscious thoughts, ideas flicker in and out of potential, and your awareness catches only the collapsed result? You don't build your ideas like bricks. You measure them, and by measuring, you make them real. The parallel is not accidental, it's poetic physics. So what do we make of this strange permission the universe grants to the improbable? That tunneling is not just a physical oddity, but a philosophical invitation. A sign that what seems solid may be fluid, what seems bound may be open, and what seems fixed in time may not be fixed at all. If particles can ignore classical time, maybe time itself is just a rule, not a law. A local condition, not a cosmic truth. And if so, then perhaps your own limits are also locale, boundaries drawn by habits of perception, not laws of nature. Quantum tunneling tells us that certainty is an illusion, that what's impossible is often just unlikely, that the future is built not on walls, but on tunnels, and that the universe, at its deepest level, is not a machine, but a gamble, one that you, me, and everything else are constantly riding. Wormholes might connect distant points in space and time. What if every road you've ever taken, every decision, every path, every connection, was just the long way around? What if space didn't play by the rules you thought it did, and what seems infinitely far away could, under the right conditions, be just a whisper away? Imagine folding a piece of paper in half so that two distant points touch. That's the classic metaphor, but the truth is even more disorienting. The universe may be full of shortcuts, not just through space, but through time itself. These theoretical bridges, called wormholes, aren't sci-fi fantasy anymore. They're solutions to Einstein's field equations, predicted by the same mathematics that describes black holes and the warping of time. And while we've never found one, the math insists they're possible, not just portals to another galaxy, but possibly to another era, a tunnel where yesterday and tomorrow rub shoulders and cause and effect become negotiable. In a cosmos that spans billions of light years, wormholes suggest that distance might be a choice, not a barrier. That linear time might be an illusion, that where and when you are might not be as fixed as you think. To understand wormholes, we first have to break reality, not all of it, just the part we think of as continuous. Einstein showed us that gravity isn't a force pulling things down, but the bending of space and time itself. Massive objects warp the fabric of the universe like weights on a trampoline. Now imagine that this fabric doesn't just curve, it folds, creases, and maybe even tears. In 1935, Einstein and physicist Nathan Rosen proposed the existence of what we now call Einstein-Rosen bridges, theoretical tunnels that could connect two separate regions of space. These would be the first mathematical representations of wormholes, places where, instead of traveling across a vast desert of space-time, you could simply cut through it. Picture two caves on opposite sides of a mountain connected by a hidden tunnel. From the outside, they seem worlds apart, but step inside, and they meet in silence beneath the rock. That's the seduction of wormholes, the defiance of distance, the bending of narrative, the leap from here to there without passing through the in-between. But these tunnels are more than travel hacks. They challenge our understanding of causality. If a wormhole connected not just points in space, but points in time, then events could, in theory, affect their own causes. The future could loop back and brush against the past. Physicist Kip Thorne once explored this possibility with colleagues, developing a theoretical model of a traversable wormhole that could be converted into a time machine if one end experienced time differently than the other. This isn't fantasy. This is peer-reviewed relativistic physics. Yet with it comes paradox. What happens if you go back through a wormhole and stop yourself from entering it in the first place? The grandfather paradox emerges, where actions in the past threaten to unravel the future that made them possible. Quantum theory might save us from these contradictions, with probabilities branching into parallel timelines. But the wormhole doesn't care. It opens anyway. Whether your passage is stable or not, whether causality is preserved or broken, is your problem. The geometry allows the tunnel to exist. The universe shrugs. Yet stability is no small matter. Most wormhole solutions require exotic matter, material with negative energy density, to stay open. Ordinary matter collapses a wormhole faster than you can blink. Imagine a tunnel that collapses the moment you step inside, crushing you between the jaws of its own geometry. That's what gravity does unless counteracted by something repulsive, something that pushes space outward. We don't know if such exotic matter exists in usable forms. Some hints arise from quantum field theory, where phenomena like the Casimir effect produce negative energy in tightly confined spaces. But that's a far cry from building an interstellar highway. Still, even the fact that such matter doesn't violate known physics is enough to keep the dream alive. It means we don't have to rewrite the universe. We just have to understand it more deeply. The question then becomes, if wormholes are possible, why haven't we seen one? Maybe they're microscopic, fluctuations in the quantum foam too small to detect. Maybe they exist only fleetingly, collapsing before we can observe them. Or maybe they're hiding in plain sight. Some theories suggest that black holes and wormholes are two sides of the same coin, that what we call an event horizon might be the entrance to a bridge leading elsewhere. In this view, falling into a black hole doesn't crush you into oblivion, but transfers you, not just across space, but perhaps across time. Of course, we'd never know. From the outside, a falling object appears to freeze on the horizon. From the inside, it may fall forever. What lies beyond that boundary remains speculation. But speculation shaped by equations we trust with satellites, GPS, and the structure of the cosmos itself. Still, there's a deeper truth here, one not about wormholes, but about us. The idea of a hidden shortcut, of a passage through the impossible, reflects something ancient in human nature. We want escape hatches. We dream of exits, not just from physical space, but from the prisons of regret, of lost time, of roads not taken. Wormholes embody this yearning. They are metaphors made mathematical, proof that the universe, at least in theory, allows for return, for undoing, for being somewhere and someone else. In this way, wormholes are not just tunnels through space-time. They are tunnels through desire, through memory, through identity. And maybe that's why they haunt us. Not because we want to cross galaxies, but because we want to bend fate, to rewrite the moment, to reach across a lifetime and touch something we thought was gone. Wormholes tell us this might not be impossible, that even the fabric of the universe is willing to be reconfigured. That distance, loss, and sequence are not absolutes, but conditions, and that under the right circumstances, the map can fold, the line can loop, the impossible can become real, not because we believed in it, but because the math said yes. Particles exist in superpositions until measured in time. You open a door. On the other side is a room, but the room is not red or blue, large or small, full or empty. Not yet. It is every possible version of itself, overlaid in silent contradiction. It becomes red only when you walk in, large only when you stretch your arms, full only when you ask what's inside. Until you look, it waits in all its forms, undecided, undivided, undefined. Now replace the room with a particle and the door with a measurement, and you've stepped into the bizarre landscape of quantum mechanics, a place where certainty is forbidden and everything is both A and not A until observed. Superposition, the crown jewel of quantum strangeness, is not just about location or spin, it's also about time. A particle doesn't simply exist in multiple states at once. It may also exist across multiple temporal possibilities, its future and past, suspended in a shimmering fog of probability. And in this view, time isn't the ticking metronome we imagine. It's an unstable wave, rippling with all that could happen and collapsing only when we dare to ask. To understand this, imagine a single photon traveling from a source to a detector. Classically, it would move along a straight path, like a bullet from a gun. But in quantum mechanics, it takes every possible path at once, weaving through space in a chaotic ballet of probabilities. Richard Feynman's path integral formulation suggests the particle doesn't choose a route until we measure it. But what if that uncertainty also applies to when the particle travels, not just where? What if its existence isn't locked to a precise timestamp, but smeared across time like a brushstroke across a canvas? In experiments like the delayed choice quantum eraser, this isn't just hypothetical, it's demonstrated. In such setups, choices made in the present appear to retroactively influence the past. A photon behaves one way if you decide to observe it now, but if you change your setup after it's already traveled, it retroactively behaves as if it knew what was coming. The timeline flexes. The particle waits in superposition, not just across space, but across time itself. In this superposed state, a particle has no definite history. It does not have a single traceable trajectory through space-time. Instead, it exists as a wave of probabilities, a mathematical cloud in which every possible outcome is encoded. Its energy, its momentum, even its identity are not fully resolved until something happens, until a measurement collapses the wave function into a specific result. This collapse is not just an informational update, it is a fundamental reconfiguration of reality. Before the measurement, the universe itself holds open every door. Afterward, one remains. And this collapse is time-sensitive. It doesn't just determine what is, but when it is. Until you look, the particle is early and late, here and there, even alive and dead, as Schrödinger so famously demonstrated with his hypothetical cat, which exists in a limbo of life and death until observed. We often imagine the cat trapped in a box of uncertainty, but the truth is, we're all in that box. We are all particles in superposition, waiting for the universe, or perhaps ourselves, to make the next decision. But the implications go further. If particles exist in temporal superpositions, then time itself must be a probabilistic field, not a linear track. And that means our familiar past-present-future framework might be nothing more than a narrative illusion. The act of measurement doesn't just reveal a particle's position in space, it may construct its position in time. In other words, time is not the backdrop of the universe. It is an emergent property, a result of collapsing potential into actuality. Some physicists argue that before a measurement occurs, there isn't even a well-defined before. There's just a mesh of entangled probabilities waiting for interaction to resolve into something like a clock tick. This casts doubt on our deepest assumptions. Is the past fixed? Is the future open? Or are they both unresolved until experienced? And if that's true, then perhaps memory is not a recording of what has happened, but a measurement that defines what did. Perhaps recollection is the same as prediction, a quantum act of collapsing uncertainty. Maybe your brain doesn't store history like a hard drive, but constructs it like a particle wave collapsing into a story. In this way, personal identity becomes a temporal wave function. You are not your past. You are the act of resolving it into a coherent now. That flickering sense of déjà vu, that eerie feeling that something already occurred, may be a glitch in this process, an overlap of possible timelines not yet fully separated. It's not that the future is influencing the present. It's that the future and present are quantum siblings, braided until choice untangles them. One of the most startling implications of this view arises in quantum computing, where qubits can exist in superpositions of 0 and 1 until measured, but they also exist in superpositions of operations, paths not yet taken, computations not yet resolved. Their potential to calculate depends on not knowing the answer yet. Only by maintaining this uncertainty do they outperform classical systems. Reality itself seems to reward this embrace of ambiguity. Certainty is computationally expensive. Ambiguity is powerful, and so it may be with time. The more we try to nail it down, the more elusive it becomes. Time, like a quantum state, resists finality until we force it to decide. Yet, despite this profound strangeness, we live our lives as if the universe is classical. We make schedules, we wear watches, we plan for the future and mourn the past. We tell ourselves that events unfold in sequence, that time is a river flowing forward. But beneath that surface lies something stranger, a sea of unmade decisions, a quantum fabric where time is not something that passes, but something that emerges. And in this sea, particles drift not forward or backward, but sideways through possibility. When we measure them, we don't just observe, they choose. And in that choosing, we choose too. So the next time you think about time, when you remember something with painful clarity, or wonder what's coming next, know this: the universe hasn't written its script yet. It's still shimmering with drafts, still undecided. And somewhere, deep in the quantum fog, particles are waiting to be measured, waiting to become real, waiting to become now. You age faster at the top of a skyscraper than the bottom. Have you ever taken the elevator to the top floor of a skyscraper and felt like you were just a little closer to the clouds, to the stars, to something bigger than yourself? What if I told you that in those brief moments you were also closer to the future? Not metaphorically, but physically. Because according to Einstein's general theory of relativity, the passage of time itself is not consistent across heights. Time, that relentless river we all assume flows equally for everyone, ticks ever so slightly faster the farther you are from a massive gravitational source, like the Earth. This means that in the time it takes you to rise a few hundred meters, in a building, you've already begun aging faster than your reflection in the lobby mirror. It's a fact so small in magnitude, yet so vast in implication, that it fractures our everyday understanding of what it means to grow older, to move through time, to exist on the surface of this blue planet. To understand this paradox, we need to revisit the idea that gravity doesn't just pull on matter, it pulls on time itself. The heavier the mass, the more space-time curves around it, creating what we perceive as gravity. But in this curved space-time, clocks don't tick at the same rate. A clock closer to a gravitational well, say the base of a mountain, will run ever so slightly slower than one perched atop it. This phenomenon is called gravitational time dilation, and it's not a theoretical curiosity, it's a measurable, observable fact. The Haffel-Keating experiment in 1971 sent atomic clocks aboard commercial airliners. When the clocks returned, they were out of sync with their earthbound twins, not because they malfunctioned, but because time had genuinely passed at a different rate. We've since confirmed this with GPS satellites, which must account for both their speed and their height above the Earth's surface in order to provide accurate positioning. Without correcting for gravitational time dilation, GPS errors would accumulate by kilometers each day. But the skyscraper example is where this abstract truth turns intimate. It means that the security guard in the lobby of the Burj Khalifa in Dubai is actually living a slightly shorter life than the executive sipping coffee on the 163rd floor. The difference is measured in nanoseconds per year, so small that no human would ever feel it. And yet, those nanoseconds matter, over geological timescales, or at relativistic speeds, or in the presence of extreme gravitational forces. These tiny discrepancies bloom into profound distortions. In the vicinity of a black hole, for instance, time may slow to such an extent that while 1 minute passes for you, decades may pass elsewhere. But even on Earth, even in your body, time is uneven. Your head ages faster than your feet. That's not poetry, it's physics. So, what does this do to our concept of time? We like to think of time as democratic, shared, universal, fair. But general relativity tells us otherwise. Time is local. Time is conditional. Time is sculpted by the shape of space and the presence of mass. And because Earth is massive and round, time curves gently toward its center. The closer you are to the core, the more it resists. The farther you rise, the more freely it flows. This means every inch of altitude you gain is not just a change in space, it's a shift in temporal velocity. In a very real sense, climbing stairs is moving faster into the future. What does that mean for our daily lives? Not much, unless you build your philosophy around it. Because in this view, experience becomes elastic. Memory becomes relative. Life becomes not a straight line, but a stretched fabric of shifting durations. And here's where it gets deeply existential. If two people can age differently just by standing at different altitudes, then what does it mean to age together? What does it mean to say, we've shared a lifetime, when your lifetime may have moved imperceptibly faster than mine? These aren't questions with practical consequences, but they fracture the illusion of uniformity. We grow up learning that time is a universal constant, but the universe itself disagrees. And the more precisely we measure it, the more fragmented it becomes. In this light, a skyscraper becomes not just an architectural achievement, but a metaphor for the hierarchy of existence. The idea that even as we live side by side, we're each experiencing a slightly different tempo of reality. The poet might say, "We're drifting apart." The physicist would nod and reply, "Yes, by about a billionth of a second." The artist sketches love. The scientist finds distortion. And somehow, both are right, because even if the difference in aging is minuscule, its reality rewires our understanding of sameness. Time isn't shared. It's interpreted, one clock at a time, one altitude at a time, one perception at a time. The past is no longer a universal backdrop, but a patchwork of clock-dependent truths. And if this is true on Earth, then what of our dreams to live on Mars, on the Moon, near neutron stars, in orbit? Each of these destinations offers not just a new home, but a new version of time. Colonizing space may not just mean expanding across the stars. It may mean diverging in age, species, or even identity. A child born in orbit may experience a life that passes differently from ours, not just culturally, but temporally. As our technologies stretch the bounds of distance, relativity guarantees they also stretch the bounds of time. So the next time you ride to the top of a tower or gaze down from an airplane window, remember, you are not just changing your view. You are escaping Earth's grip on time, however slightly. You are surfing a gentler curve of space-time. You are aging faster than the ground below. Not enough to notice, but enough to know. And maybe that's enough to shift your thinking. Maybe it's enough to realize that every step upward is a quiet defiance of gravity's hold on your hours. Because in the end, time is not absolute. Time is terrain. And in this strange shifting landscape, altitude is not just elevation, it is acceleration through the one dimension we thought we all shared. The psychological present is a construct, not a physical instant. Imagine standing at the edge of a vast canyon at dawn. The sun hasn't yet breached the horizon, but its light has already begun to fill the sky with color. A silent promise of a moment that seems to have already begun but hasn't quite arrived. Now ask yourself, when exactly is now? The moment you inhaled to start this thought? The millisecond your neurons fired when the scene before you came into focus? Or is it still unfolding, bleeding backward and forward across an invisible line you can never touch? You live your entire life in what you call the present. Yet, paradoxically, you've never actually experienced it. Not truly. Not as a crisp, infinitesimal slice of time. Instead, what you feel as now is a psychological construction, a fragile illusion created by your brain, stitching together events from the immediate past and forecasting into the near future to create a coherent narrative, a fluid moment. This present isn't a point, it's a process. It's a rolling average, a ghost image, a window of perception lagging milliseconds behind the physical world, and ahead of conscious realization. You are always just behind reality, grasping, at its shadow. The idea that the present is not a sharply defined instant but a smeared duration, a cognitively generated experience, flips our entire understanding of time on its head. In physics, we define the present as a theoretical point, infinitely small, ungraspable, but your nervous system doesn't work that way. Neural processing takes time. It takes around 80 to 100 milliseconds for your visual cortex to process an image and allow you to become aware of it. That means every time you think you're seeing now, you're actually looking at the past. But you don't feel like you're lagging behind. You feel immediate, smooth, synchronized with the world. That's because your brain compensates by creating a present moment window, roughly 2 to 3 seconds wide, during which it groups sensory input together into one fluid temporal experience. This phenomenon is called the specious present, the duration of time your consciousness uses to experience the world as a continuous now. You're not living in a point in time. You're floating in a bubble of meaning, stretched between remembered milliseconds and anticipated outcomes. Consider how you perceive music. A single note is meaningless in isolation, but a melody, a rhythm, requires memory and anticipation, the brain's ability to connect what just happened to what's about to happen. You need that psychological window to hear a song as a song. Without it, you'd only hear disjointed blips of sound. This applies to motion, language, even emotion. When someone throws a ball towards you, you don't wait for it to hit you before reacting. Your brain predicts its trajectory and fills in the blanks. When a person smiles at you, you don't wait for your conscious mind to interpret it. Your subconscious already knows what it means before you even think about it. These experiences feel like they're happening now, but neurologically, they're not. Your awareness is a reconstruction, a harmonized illusion built from delayed data, filtered through memory and shaped by expectation. But this delay isn't a flaw, it's a feature. If your brain tried to process every sensory input in real time, you'd be paralyzed by noise and chaos. By integrating information over a small window of time, your consciousness sacrifices accuracy for coherence. It edits, it blends, it makes executive decisions about what matters and what doesn't. It smooths out rough edges so that you can walk, talk, and think as if everything is happening now, even when it isn't. Think of your brain as a movie editor. The raw footage comes in disjointed, delayed, noisy. But by overlapping frames, trimming silence, adding transitions, and removing jarring jumps, the editor crafts a story. That story is your present moment. And this story varies from person to person, situation to situation. Time slows down in emergencies, it stretches in grief, it accelerates in joy. When you're in danger, your brain hyper-accelerates its processing to predict outcomes faster, and you remember the event as if it took longer. It's not time that slowed, it's memory that expanded. Athletes, musicians, soldiers, they all report entering a flow state where time seems to dilate and awareness becomes hyper-focused. What's really happening is that their psychological present has been finely tuned, sharpened, widened in some places and narrowed in others to allow maximum response in minimum delay. The present isn't fixed, it's flexible, sculpted by attention, urgency, expectation, and context. And what about people who lose this window? Certain neurological disorders can distort the perception of now. In schizophrenia, for instance, the temporal binding that normally integrates stimuli breaks down. Patients may feel that thoughts or sensations are not synchronized with reality. In dissociative disorders, people may feel time slip through their fingers, not metaphorically, but experientially. Even psychedelic states can widen or fracture the specious present, causing 1 second to feel like eternity or entire minutes to vanish. These aren't metaphors, they're empirical distortions in the brain's ability to generate now, and they remind us that what we call the present isn't real in any objective sense. It's an emergent phenomenon of neural dynamics. This has deep implications for free will, responsibility, and consciousness. If your awareness is always a fraction behind physical reality, then your decisions are being made before you consciously make them. Liebert's experiments in the 1980s showed that neural activity predicting a decision occurs before subjects become aware of their choice. Your brain begins preparing for action milliseconds before your you steps onto the stage. The present, you feel, is a post-processed moment, edited to include the illusion of choice, the illusion of simultaneity. You are not experiencing reality. You are experiencing your brain's rendering of it. And like any rendering, it's subject to latency, compression, and creative license. So what does all this mean for the way we live? It means that we are always slightly behind, that your entire life is lived chasing a phantom moment that vanishes the instant you think you've caught it. It means that presence, true, raw, unfiltered presence, may be neurologically impossible, but it also means that we are meaning-making machines, crafting clarity out of delay. The fact that we can walk through a room, hold a conversation, fall in love, or marvel at a sunset, despite never truly being in sync with time itself, is a testament not to our weakness, but to our brilliance. We are out of phase, and yet we function. We are late to every moment, and yet we create meaning from it. The psychological present is not a location on the timeline. It is a narrative device, a conscious hallucination, a brilliant lie your brain tells you to keep you sane, stable, and oriented in a world that offers no objective now. Physics doesn't define a preferred moment. Space-time doesn't pause to let you catch up. The universe flows indifferent to your lag, and still, you carve out moments. You write songs. You say, I love you. You remember. You anticipate. You call this a life. But it is not lived in points. It is lived in ripples, in smeared intervals, in beautifully delayed fragments stitched together by hope, memory, and the need for meaning. So the next time you try to be present, realize this: you already missed it. But that doesn't mean you failed. It means you're human. You are a mind chasing time. And in the chase, you create something that time itself can never define. The feeling of now. Time might be an emergent property, not fundamental. Imagine for a moment that time isn't ticking outside of you but rising within you, not a clock on the wall, but a whisper in your nervous system. Strip away the world's sound, light, and rhythm, and something terrifying happens. Time loses form. No forward, no backward. Just a dizzying stillness where change evaporates. You blink, but nothing seems to move. That flicker of unease. That's your brain, desperate to reassemble. The illusion of flow. It's like waking up mid-sentence in a book you didn't start, trying to make sense of a narrative that might never have existed. What if this strange sensation isn't the failure of your senses, but the actual truth of the universe? That, time, the very thing you count birthdays with, fear running out of, and measure your existence against, is not real in the way you think. Not a foundational feature of the cosmos, not stitched into the fabric of reality, but a trick, a side effect, an echo of something deeper, more primitive and more abstract. According to several leading theories in modern physics, time may be an emergent property, not a fundamental one. Meaning, it's not built into the universe, it's built into you. In classical physics, time is a trusted companion. Newton treated it as absolute. A silent, ever-flowing river that moved uniformly through all things, whether or not anyone was watching. He imagined a universal clock ticking in the background of reality, invisible but eternal. But that picture was shattered by Einstein. With relativity, time became elastic, pliable, something that could stretch, bend, and slow depending on speed or gravity. Time, once the ruler, was now ruled. Yet even in Einstein's world, time still had a place. It was embedded in space-time, not absolute, but still there. But then came the quantum world, and the game changed again. When physicists tried to merge quantum mechanics with general relativity to build a single unified theory of quantum gravity, something strange emerged. In some of the equations that describe the deepest layers of reality, time disappears entirely, not because it's been hidden, but because it may never have been there to begin with. Take the Wheeler-DeWitt equation, one of the most central equations in quantum cosmology. It attempts to describe the quantum state of the entire universe, and in its most complete form, time doesn't even appear, not as a variable, not as a parameter. It's simply absent. The universe, as described by this framework, doesn't evolve through time. It just is. Timeless, eternal. Not in a spiritual sense, but in a cold, mathematical one. It's like looking at a painting of every moment that has ever existed, all at once, and realizing the brushstrokes don't care about your sequence. The past, present, and future, those are your inventions, not nature's. And this leads us to something even more mind-bending. The idea that time is an emergent phenomenon, much like temperature. No single particle has a temperature. But when you collect trillions of them in motion, the collective agitation gives rise to heat. Likewise, maybe no single moment has time. But when enough systems interact, when complexity arises, when entropy increases, when change can be observed, time appears not as a thing, but as a story. Recent work in quantum information theory supports this idea. In particular, studies have shown that entanglement, the mysterious quantum link between particles, might be the key to creating the illusion of time. In a fully entangled quantum system, where all possible states are blurred into one, time doesn't flow. Everything exists in a kind of frozen superposition. But as systems become more complex and start to decohere, as entanglement gives way to separable states, a temporal structure begins to form. Like watching frames of a film emerge from static, our minds begin to see direction, sequence, and flow. In other words, time may emerge from the very act of observation and our need to interpret quantum probabilities into definite outcomes. Without an observer, without complexity, without entropy, time collapses. It's worth pausing here to realize how radical this is. If time is not fundamental, then neither is causality. The idea that A leads to B, that causes create effects, might be nothing more than a perceptual illusion. In the most basic models of quantum gravity, the universe is described as a timeless configuration space, a landscape of all possible states, with no preferred direction. Time isn't a thread woven through this space. It's a path we carve through it. Like choosing a route through a static map, consciousness moves from state to state, giving birth to time, not by observing the universe, but by constructing a narrative through it. This aligns with a broader view in theoretical physics, known as the block universe, where all points in time, past, present, and future, are equally real. The future isn't something that will happen, it's something that already is, simply unseen. We are not moving forward through time, we are revealing slices of an unchanging whole. In this sense, time is like a flashlight sweeping across a vast mural. The painting doesn't move, but the beam gives the illusion of motion, and you, the observer, believe the scene is unfolding, when in fact, it was always there. But if time is just an emergent phenomenon, why do we experience it so powerfully? Why do we measure our lives in hours and days, mourn the past, fear the future, and long for moments that slip through our fingers? The answer might lie in biology. Our brains are time machines, not in the sense of traveling through time, but in generating it. The way we store memories, predict outcomes, and process sensory input all require a temporal framework. Evolution has shaped our cognition to prioritize time because organisms that can anticipate the future and remember the past survive better than those that can't. Time, then, may be a biological adaptation, not a physical constant. This might also explain why time feels different depending on context, why a single moment can feel eternal in crisis, but hours vanish during joy, why children feel summers stretch forever, while adults watch years blur by. If time is not a universal flow but a cognitive byproduct, then its texture, its rhythm, its speed, all of it is constructed, custom-made by your brain, based on attention, emotion, and context. And this has profound implications. If time is not a cosmic law but a local illusion, then the universe doesn't grow old. It doesn't wait. It doesn't begin or end. The Big Bang might not have been the start of time, just the boundary of the region we can explain. And death? That terrifying edge of personal time. Perhaps it's just a transition to a different frame of the cosmic mural, one your consciousness no longer sweeps across, but which still exists. Time, in this view, is not a dimension to travel. It's a language, one we speak to make sense of change, memory, and meaning. The universe doesn't write in time. It writes in relationships, probabilities, fields. And we translate that script into tenses, clocks, and stories. So when you next look at a clock, realize that you're not seeing an objective truth. You're seeing an echo of entanglement, a shadow of emergence, a useful fiction that guides your life while hiding the deeper stillness beneath. And that stillness, it's not empty. It's full of everything, every possibility, every moment, every configuration that could ever be. The present isn't all that exists. It's all that you can access. Time isn't fundamental, but you are. And that makes the illusion, however fragile, beautiful. Your perception of duration changes with emotion and attention. Imagine a moment stretching like taffy between your fingertips, a second that refuses to end, like the breath you hold before a car crash, or the eternity you feel when waiting for bad news. Now contrast that with the way hours evaporate when you're laughing with someone you love, or how entire days disappear into the blur of routine. The world doesn't change. The clocks keep ticking at their mechanical pace. But something inside, you, something visceral, cognitive, emotional, bends time's rhythm. The passage of time, we believe, is universal. But what if it isn't? What if time is not just counted by machines and measured by stars, but shaped by your feelings, focus, and fear? What if the length of a moment isn't in the moment at all, but in you? Let's begin with a paradox you felt but never questioned. Why does fear slow time down? In life-threatening situations, people often report that everything happens in slow motion. Bullets crawl through the air, cars flip like ballet, seconds stretch into sentences. This isn't science fiction, it's neurology. In these high-stakes moments, the brain's amygdala, the region responsible for fear, kicks into overdrive. It begins hyper-recording details, flooding the brain with sensory data. More impressions per second mean more frames of memory, and the more densely you remember something, the longer it feels in hindsight. Your perception of time's density stretches the perceived duration. It's not that time slows, it's that your brain speeds up. But this distortion isn't limited to fear. Joy too reshapes time, only in the opposite direction. Hours spent in laughter vanish. Concerts end too soon. Summer days as a child feel infinite in the moment, yet fleeting in memory. This isn't just nostalgia talking. There's neuroscience behind it. During joyful experiences, dopamine levels rise, and with them, your brain enters a state of flow. You become immersed, focused, aware, but not of time. And without attention anchoring you to each passing second, the timeline collapses inward. Moments compress. Time, unmeasured, becomes unremembered. This subjective warping of time doesn't only happen in extreme emotions. It happens every day, during boredom, anticipation, stress, routine. When you're waiting for a message that never comes, minutes can feel like an hour. When you're stuck in traffic or enduring a dull meeting, time feels like it's dragging its feet. These aren't metaphors. They're measurable psychological phenomena. Studies have shown that attention is a key player in the perception of duration. When you're paying close attention, time stretches. When you're distracted or disengaged, it collapses. In effect, time expands in focus and contracts in neglect. Consider this. If you lived the same 24 hours twice, once with intense awareness, once on autopilot, the first would feel longer, richer, more filled. This is why time seems to move faster as we age. As children, everything is new and our attention is hyperactive. The world demands observation, but as we grow older, novelty fades. We fall into patterns, days blend, and with less attention, devoted to new experiences, time compresses. This is why years fly for adults. not because time speeds up, but because we stop noticing. This phenomenon has been deeply studied in psychology. One key theory is the contextual change model, which suggests that we perceive longer durations when our internal context changes more often. A day filled with varied experiences feels longer than a repetitive one, even if both contain the same number of minutes. In this light, monotony is a time thief, repetition is compression, and variety is expansion. The more change you experience, the longer your day feels, not just emotionally, but cognitively. There's also the concept of retrospective versus prospective timing. When you're asked to estimate how long something took after the fact, you rely on how much you remember. More memories mean a longer perceived time. That's retrospective. In contrast, prospective timing is what you feel while something is happening, and that relies more on your expectation, emotional state, and conscious attention. If you know you're going to be waiting and you keep checking the clock, time stretches unbearably. But if you're engrossed in a story, a conversation, or a task, it contracts. And here's where things get metaphysical. If time can feel longer or shorter depending on awareness, then your experience of time is a construct, not a constant. The seconds on the clock may be even, but the seconds in your mind are not. This raises a haunting idea. Your entire life, how long it feels, how rich it seems, how meaningful it becomes, is a function of your attention and emotion. The more you feel, the more you remember, the more you notice, the longer you live. Not in years, but in psychological time. This has profound implications. Imagine two people on the same calendar timeline. One drifts through life numbly, locked in habit, emotionally flat, passively scrolling, going through the motions. The other burns with curiosity, faces heartbreak and joy, dares to feel everything, and plunges into discomfort and wonder. One life feels like a sprint, the other an odyssey. And yet both were born and died on the same dates. This is the secret horror and the secret hope of subjective time. Your life is not measured in years. It is measured in depth. Even trauma reshapes this measurement. Traumatic events often lead to a heightened sense of time, not just in the moment, but long after. PTSD can make the past feel like the present, dragging old moments into the now, elongating suffering. Conversely, mindfulness practices, the act of grounding yourself in each moment, have been shown to slow down perceived time. This isn't just poetic, it's measurable. People who meditate regularly report a richer, more expansive sense of time. The clock doesn't change, their minds do, and this brings us to a chilling realization. Time is your brain's creation. There is no objective timeline etched into your neurons. There is only perceived duration, bent by feeling, carved by focus, shaped by awareness. If your perception can elongate or compress experience, then your life is not just happening, it's being composed by the very instrument that observes it. Your mind is not a passenger on time's train, it is the conductor, deciding when to accelerate, when to coast, when to screech to a halt. So the next time you find yourself saying, "Where did the time go?" Pause. It didn't go anywhere. You just weren't watching. And the more you miss, the shorter your life becomes. Not in years, but in lived experience. Because time, it turns out, isn't just counted. It's crafted, moment by moment, feeling by feeling, glance by glance. And that means something beautiful too. If you want to live longer, not in age, but in awareness, you can. Pay attention, feel deeply, break routine, embrace newness, seek discomfort. Let emotion sharpen your edges and novelty pull you out of patterns. Because in doing so, you're not just enriching your memories, you're expanding time itself, or at least the only version of it you'll ever truly know, your own. There is no edge of the universe, yet it grows. Picture a balloon, not the kind that floats from a string, but one that stretches endlessly as you inflate it, not into empty space, but into nothingness itself. Imagine standing on that balloon's surface. No matter how far you walk, you never reach an edge, because there isn't one. The balloon keeps expanding, but not into anything, just more of itself. This is not a metaphor for the universe. It's what the universe actually does. It grows, relentlessly, furiously, silently, and yet it has no boundary, no wall, no outer limit. Space doesn't expand into space. Space creates more space. And if that sounds impossible, paradoxical, or even nonsensical, good. That means your brain is still working. Let's start by confronting a deeply intuitive, but entirely wrong, idea that the universe is a kind of bubble floating in a larger space. Something with borders, a container, a cosmic terrarium. It's not. Our universe doesn't sit inside anything. There is no outside, no beyond the edge. The universe contains all of space and time. And when we say it's expanding, we don't mean it's growing into a pre-existing void. We mean that the fabric of space itself is stretching. Galaxies are not moving through space like dots on a balloon. They are being pulled apart as space grows between them. It's not motion through space, it's the expansion of space itself. This concept, called metric expansion, was born from the mind of Albert Einstein, but it wasn't fully realized until Edwin Hubble looked through his telescope and saw galaxies racing away from us in all directions. That was the first clue. The second was stranger. The farther away a galaxy is, the faster it appears to be receding. This relationship, called Hubble's law, implies that the universe is expanding uniformly. But if everything is moving away from everything else, where's the center? The answer, nowhere. Or more precisely, everywhere. You see, the Big Bang wasn't an explosion in space. It was an explosion of space. Every point in the universe was once the same point. And then that point expanded. That means every location in the cosmos is equidistant from the origin, because the origin was everywhere. The universe didn't begin over there and spread outward. It began all at once, everywhere, and grew from within itself. This is why there's no edge. The universe is not expanding into anything because there's no outside to expand into. There's just more. Now, here's the really mind-bending part. Even though the universe has no edge, it has a shape. And that shape is determined not by walls or borders, but by geometry, the curvature of space-time itself. Depending on how much mass and energy the universe contains, it can be flat, positively curved like a sphere, or negatively curved like a saddle. Current evidence suggests our universe is very close to flat, which implies it could be infinite in extent, or even stranger, finite but unbounded, like the 3D surface of a 4D hypersphere. That means you could travel forever in one direction and never hit a wall, just loop around the universe endlessly without ever encountering a boundary. But how does something with no edge grow? How can the infinite get bigger? The key lies in understanding that the universe doesn't expand in the way objects do. When we talk about the expansion of the universe, we mean the increase in the distance between gravitationally unbound objects, like distant galaxies. It's not that galaxies are flying away from each other through space, but rather, the space between them is stretching. And this expansion isn't being pushed from the outside. It's being driven from within, powered by something we call dark energy. Dark energy is one of the strangest forces in the cosmos. It's not a substance, not a particle, not a field we can detect directly. But we know it's there because of its effects. It's accelerating the expansion of the universe, not just sustaining it, speeding it up. That means the fabric of the universe is stretching faster and faster, and galaxies that are now visible will one day slip beyond our cosmic horizon. Their light will never reach us. They will disappear from view, not because they've gone somewhere, but because the space between us has grown too fast for their light to catch up. In a few trillion years, the night sky may be empty, not because the universe has shrunk, but because it has expanded so far that everything else is unreachable. And here's the cruel poetry. The more the universe expands, the more isolated we become. Space doesn't just create distance, it creates separation. And yet, that separation isn't a boundary. It's not a wall, it's just more space. Even now, some regions of the universe are receding from us faster than the speed of light. That doesn't break physics. Special relativity prohibits objects from moving through space faster than light, but space itself can expand at any speed. That's the loophole. That's how galaxies can vanish into the dark. not by accelerating, but by riding the swell of space-time like a surfer on an ever-growing wave. The edge of the observable universe isn't the edge of the universe. It's just the limit of what we can see. So if there's no edge, no wall, no outside, how do we map the universe? We use light. We look back in time. The farther we see, the older the light. The most distant light we've detected is the cosmic microwave background, the afterglow of the Big Bang itself. But even that is not a boundary. It's a veil, a curtain. Beyond it lies more stars, more galaxies, more structure. But they are forever hidden from us, their light permanently out of reach. Not because of a physical wall, but because of a cosmic silence imposed by distance and time. Now, let's go deeper. Some models suggest that space may be infinite, even though it started from a finite event. This means the Big Bang didn't happen at a point in space. It happened at a moment in time, and space has been growing ever since, possibly with no bounds at all. This opens the door to bizarre possibilities. Infinite versions of galaxies, stars, planets, maybe even you. In an infinite space, every configuration of particles will eventually repeat. Somewhere out there, statistically, may be a version of you reading these words in a universe just like this, but ever so slightly different. And still, the universe keeps growing. This has philosophical weight. We are accustomed to thinking in binaries, inside and outside, beginning and end, near and far. But the universe defies these categories. It has no outside, no edge, no center, no absolute direction. You can't go to the end of the universe because it isn't a place with borders. It's a process, a condition, an evolving field of space-time whose limits are not defined by physical walls, but by the limits of perception, causality, and light. And perhaps the strangest part of all is this. Though the universe has no edge, you do. Your mind, your perspective, your body, they're bounded. You exist within a tiny bubble of experience, confined to a moment, a planet, a perspective. The universe is growing, and you're standing still, not in position, but in scale. And yet, from your bounded mind, you can imagine the unbounded. From your limited position, you can grasp the limitless. And in doing so, you do something the universe itself cannot: reflect on its own edgeless nature. In the end, asking where the universe ends is like asking where a circle begins. It's a question born from our need for edges, for boundaries that make sense. But the cosmos has no obligation to be sensible. It only has the obligation to be. And in that being, it grows, not outward, but inward and everywhere, all at once, endlessly. Space is not empty. It's a quantum field playground. You've been lied to, maybe not maliciously, maybe not even knowingly, but lied to nonetheless. Every time you were told that space is a vacuum, a void, a silent emptiness that stretches between stars, between atoms, between the very molecules of your breath. You were told it was nothing, just a blank canvas on which the drama of matter and energy plays out. But what if I told you that the emptiest parts of the universe are actually the most alive, seething, jittering and humming with activity? That what you think of as nothing is actually everything in disguise. Space, as it turns out, is not empty. It is not still. It is not dead. It is a quantum field playground, and it's more bizarre than any fiction. Let's begin by unraveling this illusion of emptiness. In classical physics, Newton's realm, space was a backdrop, a neutral container. Objects moved through it, but space itself was passive. Even Einstein, for all his revolutionary brilliance, still viewed the vacuum as a kind of stage. A dynamic one, yes, curved by mass and energy, but still fundamentally empty when devoid of matter. But the quantum world shattered that idea. According to quantum field theory, the most precise, accurate framework we've ever developed for describing nature, every particle is a ripple in an underlying field. Not just some particles, all of them. Electrons, ripples in the electron field. Photons, ripples in the electromagnetic field, quarks, gluons, neutrinos, all just excitations in different quantum fields. These fields are not optional add-ons to the universe. They are the universe, and they exist everywhere, even in deep interstellar space, even in the vacuum of a sealed lab chamber, even in the infinite void between galaxies. The vacuum, in quantum terms, is not nothing. It's the lowest energy state of all these fields. And even that state is not truly still. Why? Because of something called vacuum fluctuations. The Heisenberg uncertainty principle tells us that you can never simultaneously know a system's exact energy and its exact time duration. That uncertainty means that, even in a vacuum, there must be temporary fluctuations in energy. Virtual particles, ghost-like pairs of matter and antimatter, pop into existence, collide, and vanish again, all in less time than it takes a neuron to fire. These are not science fiction. They are measurable phenomena. In fact, the Casimir effect, a real and tested experiment, shows that two uncharged metal plates placed very close together in a vacuum actually feel a force pushing them together. Why? Because the virtual particles in the quantum vacuum can't exist between the plates in the same way they can outside. And that imbalance creates a measurable pressure. This is not theoretical garnish. These fluctuations affect real things. The Lamb shift in hydrogen atoms, the stability of atomic structures, even the evaporation of black holes through Hawking radiation depends on the quantum froth of empty space. When a black hole sits in a vacuum, the virtual particle pairs near its event horizon sometimes split. One falls in, the other escapes. That escaping particle becomes real, robbing the black hole of mass in the process. That's right, black holes evaporate because of the quantum chaos of empty space. But it gets even weirder. The energy of the vacuum isn't just a curious side note. It might be the dominant energy in the universe. We call it dark energy, a mysterious, repulsive force that makes up nearly 70% of all cosmic energy. It's not matter. It's not light. It doesn't clump or cluster or form galaxies. But it's everywhere, in every cubic centimeter of space. And it's causing the expansion of the universe to accelerate. The best guess physicists have? That dark energy is the energy of the vacuum itself, the zero-point energy of all the quantum fields combined. The fabric of nothingness is pushing the universe apart. Now pause, take a breath, let that sink in. The stars are drifting apart because nothing is too energetic to sit still. So when we look up at the night sky and see blackness between the stars, we're not seeing emptiness. We're seeing a seething, invisible sea of potential. A latent storm of fluctuations, fields upon fields overlapping, interacting, interfering. And these fields aren't like fields of grass or wheat. They don't sit passively, they oscillate, they interact. They birth particles from their turbulence. The universe, in its quietest corners, is never quiet. Let's put this into perspective. Take a cubic centimeter of the emptiest vacuum we can create in a lab. Remove all particles, all atoms, all radiation. Chill it to near absolute zero, and still, it is buzzing. Still, it is not truly empty. Now scale that up. Consider the vast intergalactic voids, trillions of cubic light years of space. That's not emptiness. That's an ocean of quantum potential. And if we knew how to tap into it, we'd have access to energies far beyond anything our stars can provide. Some speculative theories, like those involving zero-point energy extraction, imagine future civilizations that could harness this energy, bending space-time, powering starships, even manipulating the fundamental constants of reality. It sounds like science fiction, and maybe it is. But the underlying idea is built on real physics, that space is not a void to be crossed, but a medium to be explored. And now we arrive at the deepest layer. If space is not empty, then what is reality? What is a particle if it is just a wrinkle in a field? What is a vacuum if it teems with invisible motion? Is there such a thing as nothing at all? Philosophers have long debated the nature of nothingness. Is it the absence of being, or just the absence of what we can perceive? Quantum field theory offers a third option. Nothingness is not non-being. It is unrealized being. The vacuum is not empty. It is pregnant with possibility. This flips our intuition. We once thought of space as a container and matter as content. Now we understand that space, the vacuum, is the content, and matter is just a local disturbance, a pattern, a temporary knot in the fabric of an ever-active field. You are not made of stuff that exists inside space. You are a coordinated ripple in a field that spans the cosmos. And yet, you feel solid, real. You don't feel like a wave. You don't feel like a ripple. But every electron in your body is a resonance in an invisible field that stretches from here to the edge of the observable universe and beyond. These fields don't turn off. They don't stop at your skin. They don't disappear when you die. They're always there, always humming, always ready to ripple again. So what does it mean to say that space is not empty? It means that the very stage of existence is alive in its own way. Not conscious, not thinking, but dynamically restless. It means that the idea of a quiet, passive universe is an illusion, a comforting lie we tell ourselves because the truth is too strange to grasp. It means that the most profound mysteries of the cosmos may lie not in galaxies or black holes, but in the background hum of nothing itself. And finally, it means this. Every time you look into the night sky and see the darkness between stars, you are not looking into a void. You are looking into a sea of fields, of energy, of potential, a roiling, infinite playground of quantum whispers. And somewhere in that playground, reality is still being written. The stronger the gravity, the slower the time. Imagine you're standing at the edge of a vast canyon, and somewhere far below, your shadow falls on a rock. Now imagine that the very seconds ticking in your body, your heartbeats, your thoughts, your breaths are moving ever so slightly faster than those of your shadow. Not because of movement, not because of perception, but because of gravity. Because time, as strange as it sounds, isn't fixed. It bends, it stretches, it slows. And one of the most profound truths we've ever uncovered about the nature of reality is this: the stronger the gravity, the slower the time. This isn't science fiction. It's one of the core predictions of Einstein's general theory of relativity, and it has been tested again and again, not in theoretical simulations, but in our everyday world. Time doesn't flow the same for everyone, everywhere. It's affected by mass, by proximity to massive objects, by the warping of space-time itself. What this means is astonishing. If you live at the bottom of a valley, time passes more slowly for you than it does for someone on a mountain peak. Not metaphorically, not relatively, objectively. Let's unfold this idea from its roots. Before Einstein, time was thought to be absolute, a universal clock ticking identically for all observers. Whether you were in motion or at rest, on Earth or in the stars, time was presumed to be impartial, immutable. But Einstein shattered that illusion. He realized that space and time are not separate entities. They are interwoven into a four-dimensional fabric called space-time, and this fabric can be stretched, twisted, curved by mass and energy. Gravity, in Einstein's view, wasn't a force pulling objects toward each other. It was the result of mass bending the very geometry of the universe. And where this geometry bends, time itself distorts. In regions of stronger gravitational fields, closer to massive bodies like planets, stars, or black holes, time moves more slowly compared to regions of weaker gravitational fields. This phenomenon is called gravitational time dilation, and while it might sound like an exotic concept confined to physics textbooks, it's something we actually rely on every single day. The GPS satellites that orbit Earth have to account for both their motion, which causes time to slow down due to special relativity, and their higher altitude, which causes time to speed up compared to clocks on Earth due to weaker gravity. Without these adjustments, your GPS would drift by several kilometers per day. Technology itself confirms that time is not universal, but the consequences of gravitational time dilation stretch far beyond practical engineering. Consider a thought experiment, one that's been visualized, dramatized, and debated endlessly. Imagine you're floating just outside the event horizon of a black hole. From your perspective, a clock on your wrist ticks normally, but if someone were watching you from a safe distance, they would see your time stretching, slowing, eventually freezing as you approach the event horizon. To them, you would appear to never actually cross the horizon. Your fall would slow down infinitesimally, frozen in time, like a cosmic statue at the edge of oblivion. And here's where things turn philosophical. What is now when time passes, differently for every observer? What does it mean to live in the present if your present is someone else's past or future? If two twins were separated, one sent on a journey near a massive planet and the other stayed on Earth, the traveler would return younger than their sibling. This is not a paradox. It's a measurable, observable result. Gravity changes the rhythm of your existence. Even here on Earth, this effect is not zero. Atomic clocks placed at different altitudes tick at different rates. The closer you are to the center of Earth's gravity well, the slower time flows. Live your whole life on the top floor of a skyscraper, and you'll age just a tiny bit faster than someone living on the ground floor. The difference is small, but real. The planet itself is a time machine, subtly reshaping the seconds you believe are steady. Now imagine what this means across the universe. Near neutron stars, where matter is so dense that a teaspoonful weighs more than Mount Everest, time slows to a crawl. Near black holes, where gravity becomes infinite, time essentially stops. The deeper you go into a gravity well, the more time becomes elastic. The more it resists the ticking you assume is steady. The universe is filled with zones of time tension, where moments stretch and contract based on the invisible warping of space-time. And yet, your brain doesn't feel any of this. Time to you feels consistent, flowing, linear. You wake, you live, you sleep. But beneath that illusion, the seconds are not impartial. They are being bent, sculpted, by the very structure of reality. You are moving through a web, a gravitational ocean that modulates your pace of being. Some theories go even deeper. They suggest that time might not even exist as a fundamental property. Instead, what we experience as time may be a result of the relationships between matter, motion, and information. In this view, time dilation isn't a distortion of an absolute flow. It is the only flow. Time doesn't stretch because something is changing time. It stretches because there is nothing else to compare it to. Time is what mass and energy do to each other. And that leads to one of the most profound insights you can have about your existence. You are not just a passenger in time. You are a participant in its shaping. Your proximity to mass, your motion through space, your position in gravitational fields, all determine how your moments unfold. Time is not the same for the person beside you, not exactly, and definitely not the same for the galaxies dancing at the edge of observation. So what is gravity then, if not a downward force? It is the bending of the stage on which the play of existence unfolds, and time is the rhythm of that play, sometimes quickened, sometimes slowed, but never absolute. And now, take a final thought with you. When you stand near a mountain, when you sleep in a valley, when you orbit a planet or cross an ocean, you are not just moving through geography, you are moving through time differently. Your very heartbeat stretches or contracts in ways imperceptible to you, but real nonetheless. Gravity, the silent sculptor, is slowing your seconds. In a way, you are aging differently based on where you exist, and once you understand that, you begin to see the cosmos not just as a space to explore, but as a temporal terrain, a landscape of shifting clocks, where every star, every planet, every gravitational well is a different tempo in the grand symphony of the universe. And you are the melody, shaped not by notes, but by time that flows like liquid light, pulled and stretched by the weight of being itself. The fabric of space can stretch faster than light. Imagine holding a rubber sheet between your fingers. Stretch it slightly, and the changes ripple across gently. But now, imagine pulling it so suddenly, so forcefully, that the sheet expands faster than anything that might be crawling across it. Not because the things crawling move faster, but because the sheet itself grows underneath them. That's not just a thought experiment. That's our universe. It's one of the most mind-bending truths about reality. The fabric of space, the very arena in which everything exists, can expand faster than light. And it has. In fact, it did. In the first fraction of a second after the Big Bang, the universe didn't just grow, it inflated. Not like a balloon being slowly filled, but like a balloon that suddenly exploded outward in all directions, becoming unimaginably vast in the blink of a cosmic eye. The expansion wasn't in a place, it was the place. The stage of existence itself got bigger, not by moving through anything, but by creating new where as it went. Let's unpack that, because to truly grasp this idea is to feel the edges of your imagination stretch alongside space itself. The universe is not an object sitting in space. It is space. It's not a thing growing into something else. There is no outside. There is only the stretching of the inside. This distinction matters more than it might seem. If you imagine galaxies flying apart because they're being thrown outward by some cosmic explosion, you're picturing it wrong. They're not flying through space like debris. Space itself is expanding between them. The galaxies are mostly stationary, and it's the metric of space, the very ruler we use to measure distance, that is changing. This is allowed. It doesn't break any cosmic speed limit, because the speed of light is a limit on how fast things can move through space, not how fast space itself can stretch, and stretch it does. During the epoch known as inflation, which happened in a sliver of time so small it can barely be written in human terms, we're talking 10⁻36 to 10⁻32 seconds after the Big Bang, the universe expanded by a factor so enormous it defies intuition. Tiny quantum fluctuations, those ghostly jitters at the smallest scales, were blown up to cosmic size, and those fluctuations seeded everything: the galaxies, the stars, the planets, even us. We are here because space expanded faster than light. We are the children of that inflation, but the weirdness doesn't end there. Even today, the universe is still expanding. Not as quickly as during inflation, but steadily. And what's more, the rate of that expansion is accelerating. Something, often called dark energy, is causing distant galaxies to drift away from us faster and faster, to the point where some are already receding faster than the speed of light. This doesn't mean they are breaking the rules of physics. Again, they're not moving through space. The space between is growing. This leads to an eerie implication. There are galaxies that, because of this rapid expansion, are now permanently unreachable. No matter how fast we traveled, no matter how long we waited, their light will never reach us again. Not because we're too slow, but because the path itself is being stretched faster than any journey can compensate. The map is changing while we try to walk it. It's like trying to run across a river while the bridge is being extended infinitely ahead of you. The faster you run, the longer the bridge becomes. Not only can you never reach the other side, you may not even be getting closer. This shatters many of our assumptions about distance, speed, and even communication. It means there is a cosmic horizon, a limit beyond which we cannot see. Not because light isn't trying, but because the space it must cross is growing faster than light can traverse it. Our observable universe is a bubble, not because it's bounded by matter, but because it's bounded by time and the expansion of space itself. And yet, we live within this bubble as though everything is calm and steady. We wake, we sleep, we live and die, oblivious to the fact that the cosmic fabric under our feet is stretching with every passing second. Every ray of starlight we see was emitted billions of years ago from stars that may no longer exist. Across a space that has grown and morphed and bent and expanded in unimaginable ways since the light first left. This invites deep, unsettling questions. What is distance really when the ruler used to measure it changes? What is velocity when the grid itself slides apart under you? What is a location when the very definition of where is tied to a fabric that isn't fixed? And then there's the ultimate philosophical implication. If space can expand faster than light, what does that say about causality? About determinism? Can something that happens in one place ever truly influence something infinitely far away, when the gap between them is expanding faster than influence can travel? Physicists are working through these questions, but the answers don't come easily. Models like inflation are supported by data from the uniformity of the cosmic microwave background to the distribution of galaxies. But the deeper truths are wrapped in mathematical complexity and conceptual strangeness. Even the word space starts to feel inadequate. What we're really talking about is the metric structure of the universe, a field of relationships that determines how distances behave. When we say space expands, we're saying that the way we define the separation between things is itself evolving. And if the map evolves, so does the terrain, so does reality. It gets even weirder when you realize this might happen again. Some theories predict another burst of inflation in the future, or perhaps a collapse, the opposite of expansion, where the fabric contracts, warps, folds back in. The universe might not be heading toward heat death or eternal stillness, but toward a new rebirth, a new inflation, a new reality, or no reality at all. In some models of the multiverse, inflation never stops. It happens in pockets, spawning new universes endlessly, like bubbles in boiling water. In this picture, our entire observable cosmos is just one bubble in a vast, infinite foam, a tiny patch of calm in a storm of perpetual expansion. And in those other bubbles, different laws, different particles, different time, perhaps no time at all. And what about us? What does it mean for a species of finite beings to live in a universe with infinite stretch? It means that every moment we exist is a miracle of stability, a temporary lull in a sea of change. It means that your thoughts, your memories, your dreams, your love, occur on a stage that is not fixed but fluid. The very coordinates of your being are sliding apart, and yet you hold form. You persist. That's profound, because space isn't a void. It's not nothingness. It's an active, dynamic participant in the dance of reality. It can bend, twist, ripple, and stretch. It carries the weight of gravity, the tension of fields, and the history of everything. And sometimes, in its wildest moments, it stretches so fast that light itself can't keep up. So next time you look at the stars, remember, they're not just far. They're getting farther and faster, and some have already drifted beyond forever. But the light you see now, the twinkling threads of ancient photons, it's a message from a time when the universe was smaller, calmer, closer. And in that light, you glimpse not just the past, but the true elastic nature of everything, the shape of the universe. Maybe finite, but unbounded. Try to picture nothing. Not emptiness, not blackness. True nothing. No space, no time, no edge, no center. Just absence. It's a task that bends the limits of imagination, because your mind, like mine, evolved inside a world full of boundaries. We live in rooms with walls, walk across land with edges, gaze at oceans that meet the horizon, and fly across skies under ceilings of stars. So when we ask about the shape of the universe, we instinctively reach for metaphors grounded in containers: a box, a balloon, a sphere, a bubble. Something we can measure, define, and wrap our thoughts around. But what if the universe is the ultimate riddle, a thing that has form, yet no borders? What if it's finite in size, but unbounded in every direction? This isn't poetic speculation. It's a legitimate conclusion drawn from Einstein's theory of general relativity, from the cosmic microwave background, and from the very structure of space itself. To understand it, we have to break the tether between common sense and cosmic truth. Because in the grand theatre of the universe, the stage may curve back on itself in ways we cannot yet see, and perhaps never will. First, let's ask a question that seems so simple, yet is devilishly complicated. What is the shape of the universe? When scientists say shape, they don't mean it in the way you might describe a chair or a cloud. They're not talking about outlines, but about geometry, the global curvature of space. Is space flat, meaning parallel lines never meet? Is it positively curved, like the surface of a sphere, where lines eventually converge? Or is it negatively curved, like a saddle, where lines diverge? According to the most precise measurements from the Planck satellite and other observational tools, the universe appears to be flat, to a remarkable degree. But flat doesn't mean simple. In cosmology, flatness is not just about the angles in triangles adding up to 180 degrees. It means that on average, the universe doesn't curve back on itself in any significant way across observable distances. But here's the twist. Flat doesn't mean infinite. Just like a video game screen that loops when you walk too far in one direction, space could be flat and still wrap around on itself. Let's introduce a metaphor here, one you may have heard before, but we'll stretch it further. Imagine a 2D creature living on the surface of a sphere. To them, everything is flat. They can walk in any direction without ever encountering an edge, and if they walk long enough, they'll return to where they began. They don't perceive curvature because it exists in a higher dimension. From their perspective, space is finite. It has a measurable surface area, but it is unbounded. There are no edges, no walls, no falling off into the void. That's what we mean when we say finite but unbounded. Now, expand that metaphor to 3 dimensions. Imagine if our universe were the 3D surface of a 4D hypersphere, a shape we can't directly visualize, but can describe mathematically. In such a universe, you could theoretically travel in a straight line forever and eventually end up where you started, never crossing an edge, never hitting a wall, because there is no wall. Space itself loops back, not like a circle you draw on paper, but like the space you live in bending in on itself, unseen. This is not just math for math's sake. It's a possible solution to Einstein's field equations. And it opens up staggering implications. If the universe is finite and unbounded, it may have no center, no privileged position, no master coordinate. Every point would be equivalent. There is no middle of the universe, because space isn't sitting in something else. It is the container. It's self-contained. The total volume could be finite, but with no boundary to cross. This breaks the brains of those of us conditioned to think in Euclidean terms. Where does it end? It doesn't. How big is it? Measurably large, but not infinite. Can we see the whole thing? Likely not. The speed of light and the age of the universe form a limit, the observable universe. But beyond that sphere, more may exist, even if we'll never see it. And here's another brain twister. If the universe loops back on itself, then light itself could travel in a closed path. It's theoretically possible, though not confirmed, that some of the cosmic microwave background we see is light that circled the universe and came back from another direction. We could be seeing multiple images of the same ancient galaxies, distorted and rotated. We just haven't realized it yet. So, is the universe really shaped like a donut, a sphere, a torus, a multi-connected dodecahedron? Maybe. Several models exist, and they each paint a different picture of how space can loop, twist, or repeat. But the evidence isn't clear enough to pick a winner. What is clear is this. The universe does not need to be infinite to be boundless. It can be large beyond comprehension, but still self-contained. That should change how you think about everything. Because this isn't just about geometry. It's about reality. It's about the assumption that everything must begin and end, that all things have edges. We search for borders because we want certainty. We ask where things stop, because we want to know what lies beyond. But the cosmos may offer us no such comfort. It may be a hall of mirrors that reflects itself endlessly, a loop with no exit, a path that never leads outside, because there is no outside. This touches something deep in the human spirit, our need for closure. We want to trace lines, define perimeters, box up ideas into start and end points. But the universe defies that. It offers no corner, no outer wall, no final step beyond which lies nothing. And perhaps that's why we feel so disoriented in the face of it. We are edge dwellers, thrown into an edgeless world. And if the universe is indeed unbounded, then questions like, what's past the edge, dissolve. There is no past. The edge doesn't exist. Just as you can't fall off the earth. If you walk far enough, you can't fall out of the universe. The farthest galaxies are not near the boundary. There is no boundary. There's just more of the same, looping and stretching in directions we can't point toward. Even more humbling is this. In a finite but unbounded universe, you might never escape your own position. Travel far enough, and you might return to your origin, perhaps even without realizing it. You could see your own galaxy from behind. You could wave to yourself from a billion light years away. And if space repeats, patterns might emerge. Clues hidden in the microwave background, echoes in the sky. Scientists are searching for these signs. Circles in the CMB, anomalies in large-scale structure, repeating patterns that might suggest we live in a topologically complex cosmos. Nothing definitive has been found, yet. But what's more fascinating is what this idea does to your sense of place. Because if the universe is finite, yet you can never find its edge, then you are never far from the beginning nor the end. You are always inside. There is no exit, no outside to run to, no frame to stand beyond and view the whole. We are inside the painting, not looking at it. Part of the story, not observers from beyond. And maybe that's what the idea of a finite, yet unbounded universe teaches us most. That not all things need borders to be complete. That infinity can exist within limits. That you can be contained, but still without confinement. So next time you gaze at the stars and wonder where it all stops, remember, the universe may not stop at all. It may just turn gently back on itself. A cosmic whisper folding space like a page curling back to the beginning. And maybe, just maybe, in that loop, we find a kind of endlessness that doesn't need to be infinite. Time and space are interwoven. You can't change one without the other. You've probably never thought of your life as a woven thread, stretched not just through years and decades, but also through every step, every place, every direction you've ever moved. You exist not just in time and not just in space, but in a fabric that combines the two so tightly that pulling one thread warps the other. Imagine a canvas, not painted, but bent, not flat, but curved with motion and mass. What if the very stage of existence wasn't a fixed background, but a responsive tapestry, stretching, folding, trembling, reacting to every presence, every force, every particle that stirs within it? What if time doesn't merely flow, and space doesn't merely hold, but instead, they dance together, inseparably, forever locked in a cosmic choreography that defines reality itself? This is not poetic abstraction. This is the foundation of modern physics. Ever since Albert Einstein dismantled the Newtonian clockwork vision of the universe in the early 20th century, we've come to understand that time and space are not separate arenas. They are two expressions of the same thing, space-time. And to truly grasp how the universe operates, how gravity works, why GPS satellites need to correct for relativistic drift, why black holes bend not only light but history itself, you must abandon the comforting idea of space as still and time as ticking. You must embrace a deeper truth. You can't touch one without changing the other. To illustrate just how radical this is, let's rewind to Newton's conception of reality. A universe where space is an infinite, unchanging stage and time is a universal metronome, ticking at the same rate for all observers. In that worldview, the events of the cosmos play out like clockwork, predictably, objectively, the same for everyone, everywhere. But this picture cracks when you allow for the reality of motion at very high speeds or proximity to massive objects. Suddenly, time ticks slower. Distances stretch or shrink. And most importantly, what is simultaneous for one observer is not for another. Einstein's genius was in recognizing that space and time aren't distinct at all. They're interwoven into a single continuum, and the shape of that continuum is not fixed. It is curved by mass and energy. The more massive an object, the more it warps space-time around it. This warping isn't some metaphorical bending. It's measurable, observable, undeniable. Light curves when it passes near a star. Clocks tick more slowly in gravitational wells. The orbit of Mercury precesses in a way Newton's equations couldn't explain, but Einstein's could. These aren't quirks of mathematics, they're fingerprints of reality. To visualize this, imagine placing a heavy bowling ball on a stretched rubber sheet. The sheet dips under the weight. If you roll a marble nearby, it curves inward, as though pulled by an invisible hand. That hand is gravity, but more accurately, gravity isn't a force in the traditional sense. It's the manifestation of curved spacetime. Objects follow the straightest possible path in this warped geometry. And those paths appear to us as curves, orbits, freefall trajectories. But they are geodesics, natural paths in curved space. Here's the twist. When mass curves space, it also curves time. The ticking of a clock, even the beat of your heart, the decay of atoms, the rhythm of existence, slows down in stronger gravitational fields. This isn't because the mechanism breaks or the chemistry lags. It's because time itself stretches. And the only way to account for this is to accept that space and time are not separable. They're the warp and weft of the same cosmic cloth. In special relativity, which deals with observers in uniform motion, time and space mix like the x and y coordinates of a rotating frame. When you move fast enough, your forward motion steals from your passage through time. That's why time slows down the faster you go. Not because time resents motion, but because motion is a movement through space-time, and your trajectory changes how much of each you experience. It's like climbing a hill diagonally. The more horizontal ground you cover, the less vertical rise you gain. Likewise, in space-time, the more space you cover quickly, the less time you accumulate. That's why astronauts age slightly slower than people on Earth. That's why GPS satellites, zipping above us in orbit, require constant corrections to stay in sync with our clocks. Now layer general relativity on top, the theory that handles acceleration and gravity, and the picture deepens. Mass not only warps space, it warps time. A clock near a black hole ticks dramatically slower than one far from it. If you hovered just outside the event horizon of a massive black hole for a few hours, you might return to find centuries had passed on Earth. That's not fiction, that's physics. This interplay, this unavoidable coupling, is why we speak of space-time, not space and time. And here's what's even more extraordinary. The geometry of space-time determines the motion of matter, and the distribution of matter determines the geometry of space-time. It's a feedback loop. Mass tells space-time how to curve. Curved space-time tells matter how to move. They shape each other, continuously, endlessly. But what does this mean for you? It means your body, your memories, your sense of time passing. All of it is embedded in a structure far more complex than you perceive. You don't walk through space and tick through time separately. You exist along a four-dimensional trajectory, and your every motion is a thread through space-time, sewn into a fabric that bends with your presence. You are not merely in the universe, you are part of its architecture. Even something as simple as standing still is a motion through time. And walking across a room is a change in spatial coordinates. But those coordinates are not independent of time. Everything you do is a movement through space-time, and every mass around you, your chair, your building, the earth, the sun, is shaping the very geometry through which you move. This perspective has enormous consequences. It explains why black holes exist. It's why light can bend. It's why the universe can expand without expanding into anything. Because space-time isn't sitting in something larger. It is the frame. And it's not rigid. It's dynamic, fluid, reactive. Think of a trampoline, stretched and bouncing. Now think of the entire universe as that, but in 4 dimensions. That's the reality of the cosmos we live in. And yet, despite its complexity, the interweaving of time and space offers a kind of unity. It means that nothing exists in isolation. Every second you live, every inch you move, is tied to everything else. You can't freeze time without freezing space. You can't warp space without slowing clocks. You can't exist in one without the other. They are not 2 separate puzzles. They are a single code, and you are written into it. So next time you look up at the night sky, or down at your watch, remember, you're not observing 2 separate dimensions. You're gazing into a fabric, one that bends under stars, stretches through galaxies, and folds gently around your every breath. And though we may never see the threads, we live among them, woven, entangled, unseparated, always moving forward, not just through time, not just through space, but through both. as one. The universe has no center, but is expanding everywhere. Picture a balloon, not just a balloon inflating in space, but a balloon where every point on its surface stretches, where the fabric itself grows, not into anything, but of itself. Now imagine you are a tiny dot on that surface, and so is every galaxy. As the balloon expands, you and every other dot move farther apart, not because you're racing through space, but because space itself is growing between you. Now ask yourself this: where is the center of the balloon? You might instinctively point to the middle of the rubber, deep inside the balloon, where the air pushes out. But you're not inside the balloon, you're on the surface, and from that surface, there is no center. Every point sees every other point moving away, and from every point, it appears the universe is expanding in all directions. This isn't just metaphor. This is the astonishing truth of cosmology. The universe is expanding everywhere, yet it has no center. To most minds, this feels impossible. Expansion suggests a source, a center, a starting point from which things move outward. That's how explosions work. That's how ripples in a pond behave. That's how we intuitively understand motion, as something that spreads from somewhere to somewhere else. But the universe laughs at our intuitions, because the cosmos isn't a thing in space, expanding within something else. Space itself is the thing that's growing. Let's rewind to the beginning, or at least what we currently understand as the beginning. Around 13.8 billion years ago, everything, matter, energy, even space and time, was compressed into a singularity, a state of infinite density and zero volume. But even this image is misleading, because it suggests a place in pre-existing space. The more accurate statement is this: the Big Bang didn't happen at a point in space. It created space itself. There was no outside of it, because outside had no meaning. There was no before it, because time had not yet begun. The Big Bang wasn't an explosion in the universe. It was an expansion of the universe. This is hard to grasp because we live within space and time, and we're used to motion being relative. If a car drives past you, you see it move. If you're both on a train, the car seems stationary. Everything we observe moves through space. But in cosmology, something deeper is happening. Space itself is stretching. Galaxies aren't flying away like debris from a bomb. They're being carried by the flow of space itself, like dots on that inflating balloon. And here's the part that really bends the mind, because the expansion is uniform, the same in all directions. Every observer, no matter where they are, sees themselves as the center. If you were in a galaxy 10 billion light years away, you'd look around and see galaxies receding from you, just as we do from Earth. Not because we're at the center of the universe, but because there is no center. The expansion happens, not from a place, but to all places, equally. This is confirmed by our observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang. It's the most ancient light we can detect, and it comes from all directions. With nearly perfect uniformity, it tells us that no matter where we look, the universe looks the same. It has no edge, no boundary, no special point where the Big Bang happened. The entire cosmos was once that hot, dense state. The entire cosmos cooled and expanded. And the entire cosmos continues to stretch. This raises an uncomfortable question. If the universe is expanding, what is it expanding into? The answer is nothing. Not in the sense of an empty void, but in the sense that outside the universe is a meaningless phrase. Space is not inflating into a larger container. It's not like blowing a bubble into the air. There is no air. There is only the bubble, and its surface grows not by moving outward into pre-existing space, but by creating new space within itself. This expansion doesn't push galaxies through space. It stretches the space between them. That's why galaxies beyond a certain distance are receding from us faster than the speed of light. Not because they're violating special relativity, but because the space between us and them is expanding faster than light can cross it. And beyond a certain point, the cosmic event horizon, We can never see them again, not because they're too far, but because the very fabric of space is outrunning the light they emit. So what does it mean to live in a universe with no center? It means that we're not special, but neither is anywhere else. It means that every point in the universe is a valid viewpoint, and none holds primacy. That's not just philosophical humility, it's physical reality, and it forces us to let go of certain illusions. There is no central point of creation, no cosmic origin you could visit in a spacecraft, no edge you could reach with a telescope. The universe is boundless. Not infinite, perhaps, but without borders. Even the shape of the universe resists our imagination. It could be flat, like an infinite sheet, or closed, like the surface of a higher dimensional sphere, or open, like a saddle. Each possibility implies a different fate, endless expansion, eventual collapse, or something stranger. But in each case, the expansion happens everywhere, and in none of them is there a center. This doesn't just challenge our spatial intuitions, it shatters them. It means there is no privileged direction, no north of the universe, no up or down, front or back, just an expanding field of existence, rippling outward in every direction, not from a central origin, but as a property of itself. Every cubic centimeter of space is growing, and because space contains time, so is the future. This also reframes our idea of movement. We are not moving through a static space. We are passengers in a moving medium, one that carries us outward, not just in place, but in time. The expansion of the universe isn't just something happening far away. It's happening right here, between you and your screen, between atoms, between thoughts. At quantum scales, the effect is negligible, but on cosmic scales, it defines our history. In fact, without this expansion, there would be no stars, no galaxies, no life. The early universe was too hot and dense for structure to form. Only as it expanded did it cool, allowing matter to clump together, gravity to work its slow magic, and complexity to emerge. You are here, thinking, breathing, reading, because the universe expanded. You are the product of its stretching, and one day, that same expansion may pull everything apart. Galaxies will drift beyond our reach. The night sky will grow dark. The last stars will burn out. And if dark energy continues to dominate, even atoms may be torn apart in a big rip. But that's far in the future. For now, we live in a moment of richness, of stars and structure, of light and life. So next time you gaze at the sky and wonder where the center is, remember, it's not out there, it's everywhere. The universe expands not around you, but through you. Not toward the edge, but from within. And though it has no center, it gives meaning to your place in it. Because in a universe with no privileged point, every point is precious, including this one, right here, right now, where space expands and time flows and you exist. Chronostasis. Why the first tick? After looking at a clock feels frozen. Have you ever glanced at a ticking clock, only to feel like that very first second lingers unnaturally, as if time itself holds its breath for a moment just for you? It's a strange hiccup in your perception, like the world pauses before continuing its rhythm. That unsettling stillness you experience, that sense that the first tick after your gaze lands on the clock takes longer than it should, has a name, chronostasis. And it's not just an illusion, it's a profound clue into the way your brain manufactures your experience of time. Chronostasis, sometimes called the stopped clock illusion, is more than a cognitive trick. It's a glitch in your brain's internal timeline, a quiet confession from your mind that the reality you perceive isn't assembled in real time, but reconstructed retroactively, filled in, adjusted, edited like a video timeline to give you the illusion of continuity. And when you realize this, truly realize it, the question becomes much bigger than why clocks seem to pause. It becomes a question about the very fabric of your consciousness. What is the present? How do you know what's real if your mind fills in blanks it refuses to show you? Let's begin with the mechanics. Chronostasis most famously occurs when you make a rapid eye movement, a saccade, from one point to another, such as glancing at a wall clock. During that movement, your eyes dart so quickly that your visual input would blur if not for a clever neurological trick. Your brain suppresses your visual perception during the saccade. That means for a tiny moment, around 20 to 200 milliseconds, you're essentially blind. But rather than let you experience a disorienting blackout with every glance, your brain fills in that missing information with what it thinks should be there. Here's the twist. Once your eyes land on the clock and perception resumes, your brain does something even stranger. It backdates your awareness. It stitches your current view backward in time, retroactively assigning the perception to a moment before the saccade finished. The result? The first tick of the clock feels longer, not because it is, but because your brain extended your awareness to cover the blackout, as though you were already seeing when you actually weren't. The pause wasn't in the world, it was in your mind. You weren't observing reality. You were watching a clever hallucination crafted in hindsight. This delay isn't exclusive to clocks. It's just that clocks, with their precisely measured ticks, make the illusion easier to notice. Chronostasis can happen with any sudden glance at a person, a sign, a phone. And in each case, your perception of now is subtly edited. Your brain is like a film editor working just a few frames behind, splicing together the scenes of your consciousness so seamlessly that you don't notice the cuts. Except in moments like this, when the edit becomes visible, when time stutters, and you realize the show is being manipulated. But what does this mean on a deeper level? If your experience of the present can be retroactively altered, then now isn't a point on a timeline. It's a construct, assembled after the fact. It means you are not experiencing reality as it is, but as it was, filtered, cleaned, stabilized. Your mind isn't a window onto the world. It's a projection booth, screening a version of reality that was curated for narrative consistency. And sometimes, like when you glance at a clock, the edit fails just enough to be noticed. This insight fractures one of our most trusted beliefs, that our consciousness is immediate, that what we feel, see, and hear is happening right now, with no delay. But neuroscience tells a different story. Chronostasis is just one example. Consider Benjamin Libet's experiments in the 1980s, which showed that the brain initiates actions before we become consciously aware of deciding to act. Or consider the flash lag illusion, where moving objects appear ahead of where they actually are, due to predictive processing. Again and again, the evidence mounts. Our brains are predictive. Machines, not passive receivers. They are storytellers, not reporters. Chronostasis is also a mirror to time's fluidity in our subjective experience. Think about how time flies during moments of excitement, or how it crawls during boredom. But chronostasis shows that this isn't just an emotional exaggeration. It's a literal manipulation of perceived duration. Your brain warps time to preserve coherence, just like it warps space to preserve focus. It's like editing a video in real time, splicing and stretching clips to smooth out transitions. But instead of film, the material is your very sense of being. And this illusion raises haunting questions. If your mind can't even present time truthfully for a 1-second glance, what else is being edited? What memories were rewritten to feel more linear? What conversations do you recall as seamless that were filled with gaps, stutters, rewinds? How much of what you think of as you is a retroactive composition rather than a real-time stream? If time is the medium of your identity, if every thought and memory is time-stamped and arranged by perception, then the unreliability of time perception calls into question the reliability of your entire self. In a way, chronostasis is a crack in the simulation, a moment where the illusion of now wavers, and you glimpse the machinery behind your awareness. It's the temporal version of seeing a stagehand during a play, or noticing the seams in a virtual reality headset. It doesn't break the experience entirely, but it reminds you that the experience is manufactured, that what you call reality is filtered through processes you can't control and barely even detect. Some philosophers and physicists go even further. They suggest that our perception of linear time is not just flawed, but but entirely fictional. The block universe theory proposes that past, present, and future all coexist, and our movement through time is an illusion. If that's true, then chronostasis isn't a bug. It's a glimpse of the truth, a hint that your consciousness is not riding a wave of time, but constructing a story of motion through a fixed landscape. In practical terms, chronostasis is benign. It doesn't harm you. You don't miss important events. You still react to the world effectively, but philosophically, it's seismic. It shows that your sense of now, your anchor to reality, is vulnerable. It can be bent, delayed, stretched, and worse, you don't notice unless something goes wrong. That moment when the first tick lingers, that's the only clue you get that your perception of time is not real. It's a simulation, a best guess rendering that usually runs smoothly until it doesn't. And this isn't limited to the visual system. Studies have found auditory and tactile versions of chronostasis, moments where the first sound or touch after a shift in attention feels extended. The phenomenon spans senses. It's not a glitch in one pathway, it's a feature of consciousness itself. Your mind is a composer, not a mirror. It adds and subtracts beats to make the song feel whole, even when notes are missing. But what does this mean for your lived experience? Should you distrust your senses? Not necessarily. Your brain is doing the best it can with limited data. But it does mean you should hold your certainty more lightly. That when you recall a moment or insist you saw something as it was, remember, you didn't just see it. You recreated it. You didn't live time. You rewrote it. Chronostasis teaches us that time, at least the way we perceive it, is elastic. That the boundaries of now are not fixed but negotiable. That memory, perception, and awareness are woven together, not in the moment, but after the fact. And in that realization, we glimpse something terrifying and beautiful. That we are not passive passengers through time, but active authors of it. That the present we experience is our invention. Not a gift from reality, but a story told to us by a brain doing its best to make sense of delay, motion, and the shadows of moments already past. So the next time you glance at a ticking clock and the second hand seems to hesitate, don't shrug it off as a mental hiccup. See it for what it is, a crack in your constructed now. A chance to realize that your consciousness is not immediate, not raw, not unfiltered, but crafted, like a dream you don't realize you're dreaming. And in that pause, in that frozen first tick, you might catch a glimpse of the real engine beneath your awareness. A mind not designed to reveal the truth, but to make it feel seamless. You're not watching time. You're watching a version of time painted on the inside of your skull. And sometimes, just for a second, the paint drips. The Planck time. The smallest possible slice of time. Imagine trying to take a snapshot of time, not a second, not a millisecond, not even a nanosecond, but something infinitely smaller. Smaller than your brain can picture, smaller than any current instrument can measure. It's like trying to bottle the very first flicker of reality, the absolute beginning of a tick, so fleeting that the universe itself hadn't yet drawn a breath. This is the realm of the Planck time. A number so small that it defies comprehension, and yet so fundamental that it may be the very scaffold upon which our entire understanding of physics is built. Defined as roughly 539 x 1044 seconds, the Planck time is considered the shortest meaningful unit of time. A slice so fine that to go smaller would be to enter the domain where the smooth fabric of space-time begins to fray into quantum chaos. But what does it really mean to say something is the smallest unit of time? Can time be pixelated like an image on a screen? Is our universe composed of indivisible frames, like a cosmic film reel flickering forward with each Planck moment? Or is this just the edge of our scientific language, beyond which we must step into the abyss of speculation and reimagine time altogether? To understand the gravity of Planck time, we need to first accept a simple, yet deeply unsettling truth. Much of what we experience as continuous may not be continuous at all. The world feels smooth, our lives flow, seconds tick rhythmically, motion blends without interruption. But just as a high-resolution photograph is made up of millions of individual pixels, what if time itself is composed of discrete intervals? The Planck time emerges not from human imagination, but from the synthesis of the most foundational constants in physics: the speed of light, c, Planck's constant, and the gravitational constant, g. When combined through dimensional analysis, they yield a time so short that it represents a natural limit, a point beyond which our physical theories collapse into nonsense. Below the Planck time, quantum fluctuations in space-time become so violent, so chaotic, that traditional notions of cause and effect dissolve. General relativity fails. Quantum field theory trembles. We are left with a terrain where time and space are no longer separable, where before and after may lose all meaning. In this pre-geometry of the cosmos, time could loop, fork, freeze, or even cease to exist. The Planck time is thus not merely a number, it is a conceptual boundary, a veil drawn over the face of ultimate reality. Now, think of the earliest moment of our universe, the Big Bang. Our theories allow us to trace cosmic history back to a point about 1 Planck time after that event. Before that, we simply don't know. Our equations stop working. We are effectively blind. This isn't because we're lazy or unimaginative, but because the rules we've built our models upon no longer apply. The Planck era, those first fleeting instants, is where quantum gravity must reign. This is the theoretical domain that physicists dream of decoding, the realm where time may not even be a dimension in the way we experience it. The question then becomes, if time itself doesn't make sense below the Planck threshold, then is time a fundamental aspect of reality? Or is it emergent, an illusion born from deeper, more abstract layers of physics? Some models, such as loop quantum gravity and causal dynamical triangulations, attempt to model space-time as composed of tiny, indivisible units, chunks that behave more like a granular lattice than a continuous fabric. Others, like certain interpretations of string theory, suggest that space-time itself may arise from something even more primitive, like vibrating information fields or mathematical symmetries. In such views, time is not the canvas, but the painting itself, something born out of patterns and interactions, not something that exists independently. What's haunting about the Planck time is not just its brevity, but its finality. It's a cosmic speed limit for time itself. Just as the speed of light is the fastest that information can travel, the Planck time might represent the fastest that events can be meaningfully said to occur. Anything faster, any slice thinner, and we enter a domain where time as a measuring stick no longer applies. Imagine a film reel where each frame is 1 Planck moment. To a human eye, the motion appears smooth. But if you could somehow slow down your perception by a factor of 1044, you might see that reality itself jumps, clicks, blinks into being with each quantum tick. This invites philosophical dilemmas as well. If there is a smallest unit of time, then what happens in between Planck moments? Is there a void? A pause? Or is this simply a meaningless question, like asking what is north of the North Pole? The Planck time doesn't just challenge physics. It shakes the foundation of our intuition, our sense of continuity, and the very notion of happening. This also resurrects ancient questions in modern clothing. Philosophers have long debated whether time is real or simply a convenient measure of change. Thinkers like Parmenides denied the reality of time altogether, proposing that change is illusion. In modern times, the block universe theory suggests that past, present, and future are equally real and eternally fixed, a viewpoint surprisingly compatible with certain interpretations of relativity. But when we speak of the Planck time, we enter a territory that seems to dissolve even these perspectives. If time doesn't exist below a certain scale, then what does that say about causality? About identity? About memory and experience? Could our minds be bound to perceive a smooth temporal stream simply because our biology operates well above this threshold? Maybe consciousness is not designed to perceive the gaps, the quantum flickers, the granular throb of time's substructure. Maybe the illusion is a feature, not a flaw, a necessary simplification that allows us to function within a reality we can never truly grasp. So where does that leave us? The Planck time may be a technical limit in physics, but it is also a poetic one. It marks the boundary between what can be known and what must be imagined. It's the timestamp on the birth certificate of our universe, and perhaps the last readable entry in the cosmic diary before the ink vanishes. When you look at your watch, when you feel a moment pass, realize that underneath all of it, beneath the ticking of seconds, the flow of hours, the turning of years, there is a rhythm you'll never hear, a beat too fast for any heart, too faint for any mind. It's the pulse of the void, the hidden tempo of creation itself, and perhaps, just perhaps, within that tiniest of moments, the entire history of the cosmos already sleeps. The present is relative. There's no universal now. What if I told you that the now you're living in, this exact moment, this breath, this heartbeat, this awareness, might not exist for someone else, even right now? That your present is not some cosmic agreement, not a shared stage upon which all things unfold, but a deeply personal hallucination, a relative bubble of time that shifts depending on where you are and how you move. What if the idea of simultaneity, the belief that things happen together at the same time everywhere in the universe, is not only false, but physically impossible? This isn't a philosophical puzzle. It's the bedrock of modern physics, and it means that the universe has no master clock, no universal now, no absolute frame of reality to tether our moments together. Every second you live is yours alone, and this changes everything, from how we define reality to what it means to be connected at all. To understand this, let's start with the most intimate thing you think you share with others, the present. You assume that when two people clap hands, their hands meet at the same moment, that when astronauts wave at Earth, they're waving to you, now. But if you dig into the physics, that assumption crumbles. In 1905, Albert Einstein cracked the illusion wide open with his theory of special relativity. He discovered that time is not fixed. It stretches and contracts depending on how fast you're moving. But even more unsettling was what followed. Simultaneity is relative. That is, two events that appear to happen at the same time in one frame of reference might occur at different times in another. A train passenger and a person standing on the platform will not agree on what's happening now. For one, the lightning hits both ends of the train at once. For the other, it doesn't. They are living in different versions of now. This isn't some quirk of perception. It's a provable, testable, measurable feature of space-time. Consider this. Two stars explode in different galaxies, and their light reaches your telescope at the same time. You might assume they exploded simultaneously, but that assumption depends on your motion relative to them. Another observer, moving differently through space, would place those explosions at different times, one before the other. There is no cosmic referee, no intergalactic judge to say who is right. Both are valid, both are true. In this universe, truth bends with motion. To picture it, imagine reality as a vast loaf of bread, a block of space-time. Your now is a slice through that loaf. But the angle of the slice depends on how you're moving. For someone moving differently, their slice cuts through different parts of the loaf. Their present overlaps your past or your future. And yet, to them, it's still now. There is no single way to slice the loaf that everyone agrees on. This is the relativity of simultaneity. Time is not universal. The present is not objective. The illusion that we all live in the same moment is just that, an illusion. Now take this further. If there's no universal present, then what does that say about our understanding of cause and effect, of memory and intention? If two people can disagree on the order of events, who gets to say which came first? Fortunately, the laws of physics are constructed to preserve causality. No observer sees effects happen before causes in their own frame. But that's a local truth, not a global one. The order of distant events can flip depending on where you stand and how fast you're going. In other words, the universe doesn't care about your timeline. It has no preferred version of history. Everything is relative, even the present. Let's bring it closer to home. Think of GPS satellites orbiting Earth. They're essential for navigation, but they wouldn't work if we didn't account for time relativity. Because they're moving fast and sitting higher in Earth's gravity field, their clocks tick differently from clocks on the ground. The system must constantly correct for this skew, or your location would be off by kilometers. This isn't theoretical, it's practical. Your phone proves relativity every time you use Google Maps. The satellites live in a slightly different now, and engineers must constantly translate between your frame and theirs. And what about astronauts on the International Space Station? Moving at over 17,000 miles per hour, they experience time slightly more slowly than we do. But not only that, their present doesn't align perfectly with ours. From their frame of reference, events on Earth might occur in a slightly skewed order. The same handshake, the same phone call, might have a different timestamp. It's as though the fabric of time itself ripples gently with motion. As if reality is not a synchronized orchestra, but a swirling cloud of melodies playing at slightly different tempos. But if the present is relative, what does that do to our sense of togetherness? If you and I cannot agree on what now means, are we ever truly sharing a moment? Or are we always alone in our private slices of time, brushing past each other like ghosts? The emotional weight of this question is heavy. We long for synchrony, to feel with someone, to share sunsets, silences, sentences. But physics tells us that perfect temporal alignment is a myth. Even light takes time to travel between us. Every smile you receive, every voice you hear, is a relic from the past. And yet, that doesn't make them less real. It makes them more precious. Think of lovers separated by light years in a science fiction novel. One sends a message, knowing the other will receive it years later. In their frame, that message is happening now. For the recipient, it arrives in the future. But both believe in the bond. The absence of a universal present does not destroy meaning. It deepens it, because connection persists not in simultaneity, but in intention, in shared narratives that transcend time's relativity. Even on Earth, time zones hint at this disconnection. Midnight in Tokyo is morning in London. We pretend to live on one Earth, but even that is fractured into 1,000 nows. We try to coordinate, to agree on meetings and messages, but underneath the surface, each heartbeat is time-stamped by its own velocity and gravitational well. The idea that we all exist in one present moment is a social convenience, not a physical reality. And here's where philosophy enters. If there's no universal now, then perhaps now is not something we live in, but something we construct, a product of consciousness. The brain, needing order, carves out a window of awareness, a zone where inputs converge into a sense of presence. This psychological present is flexible, fuzzy, and personal, and it doesn't have to align with anyone else's. In fact, it can't. So where does this leave us? It leaves us in a universe that is far more fluid, fragmented, and fascinating than the one we were taught in school. A universe where time is not a line we walk together, but a web of frames we drift through, individually, subjectively, eternally, misaligned. And that's not a reason to despair, it's a reason to marvel, because in this fractured cosmos, we still find ways to meet, to wave across space-time, to write letters that arrive late, but land with love. Perhaps the lack of a universal now is not a flaw, but a feature, a cosmic permission slip to write our own timelines, to craft meaning not from perfect synchronicity, but from shared wonder. After all, the SDI, your brain delays reality to build a coherent now. It doesn't begin with a question or a moment of doubt. It begins with a lie your brain tells you over and over, so convincingly that you believe it without resistance. That what you're experiencing right now is happening right now. That the sound you hear, the face you see, the hand you raise, and the thought that follows are all unfolding together, in unison, in the present. But that's not what's happening, not even close. You are not reacting to reality as it unfolds. You're reacting to a version of reality that has already occurred, one that your brain has paused, filtered, rearranged, and stitched together like a film editor racing to keep up with live footage. And this is not speculation. It's neuroscience. Your brain is not a real-time processor. It is a storyteller working with delay, and the now you live in is a carefully constructed fiction. Not a reflection of the world, but a shadow of it, rendered just late enough to make it feel continuous. To understand why your brain delays reality, you have to consider the overwhelming chaos of raw sensory data. At any given instant, your eyes are taking in light that reflects from countless surfaces. Your ears are absorbing pressure waves from hundreds of directions. Your skin is registering heat, vibration, texture, pain, and all of it arrives at slightly different speeds. Touch signals travel more slowly than auditory ones. Visual data has to travel through your retina, cross synapses, and be interpreted by multiple cortical areas. Each sense lives in its own latency bubble, each signal arriving at a different moment. If your brain simply passed all of this information to you as it arrived, your experience of the world would be a disjointed, noisy stutter, like watching a movie with broken audio and mismatched subtitles, trying to follow a conversation where none of the characters speak in sync. But that's not what you feel. You feel smoothness, continuity, a seamless flow of events. That illusion, the coherence of the now, is the result of a subtle but powerful trick. Your brain waits. It pauses incoming data just long enough to synchronize it, to line up the sounds with the images, to make the touch align with the sight, and then it releases it to your conscious awareness. That moment, that unified perceptual package, is what you call the present, and by then, it's already over. This delay is measurable. In controlled experiments, scientists have found that your brain takes approximately 80 to 120 milliseconds to generate a conscious experience. That means when you think something is happening in the moment, it actually happened a tenth of a second ago, long enough for a hummingbird to flap its wings more than 10 times, or for a bullet to travel dozens of meters. But the delay doesn't feel like a delay because your brain cheats. It holds back faster signals to wait for the slower ones. When someone claps their hands in front of you, your eyes see the movement before your ears hear the sound, but your brain delays the visual perception to match the auditory one. It sacrifices speed for coherence. In essence, it rewrites the timeline of your reality, editing the order and alignment of events to produce a smooth narrative. The present isn't when things happen. It's when your brain tells you they happened. This has profound implications for your sense of self. You imagine yourself as an agent, acting in the present moment, choosing, reacting, experiencing. But if every thought, every perception, every sensation is based on delayed data, then you are not living in the moment. You are living in the after image of the moment. Your choices are not made with fresh information, but with slightly stale input. You are piloting your life with a lag, making decisions based on echoes. And what's more, your brain doesn't just delay, it predicts. Because the delay would otherwise leave you too far behind to interact effectively with your environment, your brain begins to anticipate. It guesses where the ball will land, what word will come next, how the melody will resolve. Your perception of reality is not just delayed, it's partially hallucinated, a best guess overlaid onto incomplete data, projected forward to mask the lag. You don't live in the present. You live in a blend of past and prediction. The most striking example of this can be seen in the phenomenon known as the flash lag effect. When a moving object and a stationary flash occur at the same moment, you perceive the moving object as ahead of the flash, even though they were technically simultaneous. Your brain has predicted where the moving object will be, but the flash, being unexpected, arrives unprocessed. The result is a perceptual discrepancy, a glitch that reveals the system behind the curtain. Your brain is not showing you the world as it is. It's showing you the world as it expects it to be. Like a weather forecaster who blends yesterday's data with tomorrow's guesses and delivers you the illusion of right now. Even your sense of agency, the feeling that you are in control, is affected by this delay. In Liebert's famous experiments, participants were asked to move their hand whenever they felt the urge, while their brain activity was monitored. Astonishingly, the brain began preparing the movement hundreds of milliseconds before the participant was consciously aware of deciding to act. That means your brain begins acting before you, the conscious self, makes a decision. Combine this with the delay in perception, and the reality becomes more unnerving. Your awareness is not the source of your actions. It's the narrator, arriving after the fact. building a story around what already happened and labeling it as will. You are not the author of the moment. You are the editor, rearranging frames, adding voiceover, smoothing transitions, and believing, quite convincingly, that you lived it. But perhaps the most poetic example of delayed perception lies in a phenomenon called chronostasis, often referred to as the stopped clock illusion. When you shift your gaze to a ticking clock, the first tick appears to last longer than the rest, as if time briefly froze. What's really happening is that your brain is backdating your perception to cover for the delay in shifting focus. It fills in the gap by stretching the first moment it sees, creating the illusion of a longer now. It is not content to leave blanks. It needs the world to feel continuous. It edits even the empty moments, even the silences. Your now is a patchwork of corrections. So what does this mean? To live in a reality that's always just behind the curtain. What does it mean to be a creature that experiences the world only after it's been smoothed, delayed, and compressed into coherence? It means that your sense of immediacy, of presence, of being here, is not a direct window to the world, but a cinematic projection designed for stability. It's efficient, it's reliable, and it's entirely artificial. The brain you trust to be your guide through reality is less of a reporter and more of a filmmaker, obsessed not with accuracy, but with flow. And the cost of that flow is truth. But here's the strange part. The illusion works. If your brain were truly late and made no effort to compensate, you'd stumble through your environment, always slightly behind, like trying to dance to a song you can't quite hear. Instead, you move through life with grace, catching things, dodging obstacles, reading expressions, all because your brain has become a master forger of the present. It fakes coherence so well that you can't tell it's fake. It cheats, but it cheats with such elegance that the forgery feels more real than the fragmented, chaotic data it's hiding. And maybe that's the lesson here, that the mind, in its need to impose order on disorder, builds a world that isn't true, but is useful. The now you inhabit may not be accurate, but it's stable. It lets you function. It lets you trust. It lets you love and plan and dance and think. And maybe reality doesn't have to be real to matter. Maybe the truth, filtered through delay and prediction, still holds meaning. You are always lagging behind, but you are also always catching up, always reassembling the scattered pieces of the world into something you can call now. So the next time you look up from your screen and feel the moment pass through you like wind, remember, you didn't catch it. You never do. You caught the echo, and yet it was enough to move you.